Okay, let's start. I would like to welcome you to the Linux Plumbers Conference System Boot and Security Conference. First of all, many thanks to our sponsors. Please remember about our anti-harassment policies. I will be leading this microconference together with Michał Żygowski. Matt Garrett will help us also. He will be taking notes during all sessions. However, if you want to help him, just get in touch with Matthew. A few things before we start. We have a full schedule with very interesting talks. So to avoid delays, please do not overrun your time slot. We'll be notifying you when your time ends using these cards. I will be showing like that. If you do not speak, please keep your camera turned off and microphone muted. If you want to speak, please speak up. Please turn on your camera and unmute your microphone. Only one person should be speaking at a time to avoid making noise. And of course, feel free to use chat to exchange your ideas during the talk. And last but not least, before we start, are there any questions, suggestions, something like that? We start the first presentation 7:10 PDT. So we have some time for some questions, general questions with regards to this track. Okay, so let's wait until 7:10 PDT, and then we start with first presentation from Daniel Axtens. Okay, let's start. We have 3 Daniels presenting today, I think. So the first Daniel opens our session. Daniel extends. Sorry if I misspelled your last name.
Right. Very good.
Right? Oh, thank you. Perfect. Sometimes it's difficult. So Daniel will be presenting a secure boot with UEFI, booting VMs on PowerPC. So over to you, Daniel.
Thank you. All right. So yes, I'm talking about VMs on PowerPC, and we don't have UEFI on that platform, and we'd like secure boot. So we'll talk about some of the challenges that gives us and some of the solutions that we want to propose. So I will be covering a bit of necessary background. So what do I mean by PowerPC and what does Grub think of that? PowerPC IEEE 1275. And we're going to be using a lot of appended signatures. So we're going to talk about that a little bit. Then, of course, we need our 2 steps to get secure boot. We need to go from Grub to firmware and from firmware to Grub and Grub to Linux. So we'll be talking about those steps and how we're going with upstream. I'll be asking for questions at a couple of points and comments and that sort of thing, but feel free to pop in at any time, especially if there's something that you think is confusing, because it probably confuses other people as well. So the first bit of background that I want to cover is what Grub calls PowerPC IEEE 1275. So this is how we boot some things. At high level, it's an open firmware environment. So it's based on IEEE 1275. It's more fully fleshed out in a standard called the Power Architecture Platform Reference, or PAPR. And so you call out to open firmware to do your I/O, you call out to open firmware to write to your console, that sort of thing. Notably for our purposes, we've got a 32-bit big endian ELF bootloader. And that is usually stored on something called the prep partition, which is a little slice of disk. Notably, the prep partition does not contain a file system. So usually we just blat the binary onto the disk and it's loaded directly off the disk, starting at the beginning. So this is a sharp contrast to UEFI, where our bootloader is a PE executable and it often lives on an EFI system partition, which has a file system. These distinctions are going to come up a couple of times for us. We care about this because the PowerPC IEEE 1275 plus Grub thing is used to boot virtual machines, or also known as logical partitions, on modern power servers. Now, this is an environment we care a lot about because a lot of our big, and IBM, a lot of our big enterprise systems ship with a firmware hypervisor, and the customer workloads all run inside of LPARs. So this is a use case that comes up quite a lot for us. We do also have bare metal Linux machines. They're sold on the OpenPower brand. They boot differently. We're specifically talking about virtual machines under KVM or LPARs under PowerVM. So PowerPC IEEE 1275 is one thing. Other thing that's particularly important to us is this thing called appended signatures. So appended signatures sort of rose to prominence as a way to sign Linux kernel modules. So you take, and they're used across all platforms for this, this is not power specific. You take a big chunk of data, you take your module, you hash it with some algorithm, SHA-256, you sign that with a key of your choosing, and that goes inside a PKCS7 message, which is a cryptographic standard related to, used in sort of SMIME. That's not especially exciting. So that stuck into a PKCS7 message. We then stick some fixed size metadata at the end of that. Get my hands in the screen. And then we stick a little magic bytes thing after that, which just says module signature appended. So we build it up from top to bottom. So data, crypto message, metadata, magic bytes. But then we parse it sort of back to front. So you go to the end of the file, you say, is there a module signature? If there is, you then read the fixed size metadata. The fixed size metadata tells you that it is a PKCS7 message and how big it is, and you use that to get the PKCS7 message. You parse the PKCS7 message for the hash and the key, and you can use that to verify the data that you've signed. So this is used, as I said, for Linux kernel modules. It's also used to sign kernels. And so you can verify, for example, when you're kexecing a kernel, IMA can verify an appended signature. As it turns out, OpenPower boots with kexec, and so distros are already signing their PPC64 LE kernels with appended signatures for OpenPower Secure Boot. So PowerPC IEEE 1275 is our Grub environment. Appended signatures are this thing here, and these are the things that we're going to need to secure our steps from firmware to Grub and Grub to Linux. I will pause very briefly in case I have explained appended signatures unclearly, because they're important. Right. So the first step I want to look at is Grub to Linux. And Grub to Linux, I have to click on the slide advance. So the way as I said, our kernels are already signed with appended signatures. So what I'd like to do is to teach Grub to verify appended signatures against an X509 certificate that we preload. So I want to use existing Grub features and concepts. So the verifier interface is very good. Already you can do the old school PGP verification. You can do the shimlock stuff for UEFI Secure Boot. So we want to make another one of that does appended signature verification. And also borrow the way that PGP keys can be embedded in Grub, use something very similar to embed X509 certificates. Also, because I want to stay humble about my ability to write security critical code, and especially security critical code in C, we are trying to write as little of that as possible. So PKCS7 messages and X509 certificates are stored and sent around in ASN1 serialization. Rather than writing a new ASN1 parser, I'd like to import libtasn1, which is a existing, well-tested, fuzzed, etc. C ASN1 parser. ASN1 is not self-documenting, so we need some information about how to, what fields are what, and we borrow that from GNU TLS, and then we use the existing gcrypt code to do the actual maths. So all up, this means we can get this functionality in something like, so the code in the Grub runtime, excluding stuff we're importing from other projects and excluding tests, is about 1,500 lines of code. So it's not an especially large feature, and I'm still in the process of refactoring it and cleaning it up, so that will make it a bit smaller when I'm done as well. I do have some demos of this, but I am going to come back to them at the end if we have time, because I don't want to show flashy pictures and then not have time for people to ask questions about other things. So this covers Grub to Linux. We still have to cover firmware to Grub. Before that, I'm just going to read the comments. Yes, we don't want to use, we don't want to have extra sets of signatures. And two signature schemes would be very unpleasant. Any questions on this before I move on? Okay, no webcams have popped up, so I'm going to move on. The next thing that we need to do is get to Grub from firmware. We have a few hard requirements, one of which is we need backwards compatibility. So we need a signed Grub, however we end up signing it, to still be readable by old school firmware. We are not able to completely re-engineer our boot process on the fly. Ideally, we'd like to stick with existing signature schemes and key infrastructures, so we don't want to be reinventing the wheel there. We are an ELF binary, so we can't use a PE authenticode signature. So we need something new. One thing that we are considering we would like to propose is basically to use an appended signature. There are some tricky things about this. So we want it to be a appended signature that is parsable by normal tools, looks like an appended signature, it's a real appended signature. The tricky thing about that is that when we load, firmware needs to know that an appended signature is present, and that's quite tricky because when we load Grub from the prep petition, there's no file system. No file system means no file size. No file size means no end of file. So we can't just sort of skip to the end and parse upwards because the end isn't a concept with much meaning. We can't, so what we can do is we can read the ELF header and sort of figure out the size of the ELF binary and go to the end of that. We can't, unfortunately, just keep scanning because if you have an old signed Grub and then you DD a new unsigned Grub into your prep petition, you will keep scanning and you'll hit the old signature and that will fail to verify. And then you'll tell your sysadmin that their Grub is invalidly signed. But what you should be reporting is their Grub isn't signed at all. So we can't just keep scanning. We also can't go to the end and skip forward by some fixed amount because the length of this PKCS7 message depends on your hashing algorithm and it depends upon your the metadata of your key itself. James has asked a question about the Linux kernel is built for ELF. We add a PECOF header for EFI. I don't really want to start introducing authentic code into the PowerPC flow. Any part of that process, got very strong feedback from our maintainer about that for the kernel. And so if we're not using it for the kernel, I'd like to try and keep things consistent. So appended signatures, what I propose to do to solve some of our problems. So we want, as I've said, an ordinary appended signature. And I want also, part of our maintainer feedback, an ordinary appended signature that usual unmodified tools understand. We also want, ideally, all the data to be within ELF structures. So what I am proposing to do is to add an ELF note. So a note section at the end of the binary, a little program header to say that the note is present. That note will have a type, which I'm proposing to just be the ASCII asig. It'll have a name, which is appended signature. And in the note description, we chuck the appended signature. That has to be aligned to 4 bytes because we're 32-bit ELF. So if there is any padding, we put it right up the top there before the appended signature so that the appended signature is always right at the end. And this means that we have something that's a valid ELF file. We have a valid appended signature, and we have the ELF header tell us correctly where the appended signature lives. I'm going to read those comments in a moment. I'm just going to press on for a little bit and then come back to them. If we do that, there is some signing. We sign an empty file to figure out the signature size. We reserve the space for that. In order to make sure that we always have a valid ELF file, we pad that with zeros and then truncate them away and sign them. This all works beautifully. The demos are available. What I want to do, yes, we'll come back to upstream status. I want to have a look at the comments here. If anyone wants to pop on the webcam and explain it in slightly more detail, that would be helpful. It seems to be more about PECOF.
So I think can you hear me?
Yes, go ahead.
Okay. I think what's weird here is, so one of the big problems with Authenticode, and particularly the thing Linus really didn't like, is that we wind up having to have a part of the ELF header that changes based on having the signature, which we don't have with the Kmod signatures right up until you added an ELF note.
Yes. We do have to add something because we need some way of figuring out that an appended signature exists. And that is the adding the ELF note means that we don't also have to teach all of our firmware about PECOF headers, and in particular, it means that we have nice features for backwards compatibility because ELF parsers know to ignore ELF notes that they don't understand.
Yeah.
So yeah, I guess I
think we're in agreement. I think we're just understanding.
Okay, right, good. Yes, sorry,
Yeah, it's not like I'm saying that just because we have nodes that we will suddenly start using them for the kernel modules as well and blah, 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 because I think this is restricted to Grub image only. I'm just slightly concerned that if you're using an ELF node for the signature, that you can still create sections after that node. And
So
potentially,
I think we should absolutely define that as, this is our own private part of ELF, and we're saying if you do that, you are wrong, it does not verify, because there are numerous bugs when you do that part with Authenticode. Some of them are terrifying, like you can change this to the entry point to the binaries inside the signature.
yes, so a compliant firmware must ensure that if there is an appended signature, note that it is the last section in the binary. But that means that that's sort of all you have to ensure. You don't have to muck about with anything else. And yes, I'm only proposing this for Grub. I'm not proposing that we do anything with Linux modules. I really like things to be like, I don't love the fact that we need to add something, but I want something where we can tell firmware where to find the signature, and this seemed like a reasonably nice way to do it. James.
I was going to say, to be clear, I'm not presenting Authenticode as the best solution ever. In fact, as Peter has said, it's a pretty crap solution. The only point about Authenticode is it's a standard one, because ARM is now using it and x86 is now using it.
Yes, ARM and x86 are also both using UEFI.
Well, actually, ARM is not using UEFI. That little S805 board you got in the post, it actually U-boot emulates UEFI and then it boots through EFI, but the ARM board itself has no UEFI apart from the U-boot emulation on it. I'm not, again, presenting this as a good solution. I'm just saying it's what ARM has done to get UEFI out of the box on certain of their systems. Anyway, sorry.
Yeah. I mean, yes, so potentially we could teach firmware how to implement enough of UEFI to parse a PECOF binary and validate the signature for it. But that seems a lot more terrifying than teaching it how to verify an appended signature, because we don't want any of the other UEFI bits. That's sort of been the long-standing position of Power, for better or worse, is that we don't do UEFI.
And I don't think, unless you're prepared to use a lot of the existing UEFI code, either from EDK2 or U-boot to do that, I don't think you want to implement it yourself again, or else you're going to spend some time in the bug farm.
Yes, and we also have our closed source open firmware implementation is largely in Forth, and I don't think that team would be happy if I asked them to pull in huge amounts of code to do this sort of thing.
Okay, just a quick question. How would you dual sign if I need to append multiple signatures?
What do you mean by dual sign? So I have more than one key attest to the integrity of the binary?
Yes.
Which, in practice, you really, really, really do need.
Okay. They could both live in the PKCS7 message. There is not currently, like sign file doesn't do this for you. So I will send you some mail about dual signing.
Right.
Yeah.
Authenticator allows that, but also allows a different method, which is that the signature section is just an array. I recommend the array version because people can wrap their head around it a whole lot easier.
Okay. That's interesting. Yeah, I don't understand the use case for dual signing.
When you need to cycle keys, you want some overlap time where something's signed by both.
Okay.
Or, for example, you have a public key which trusts by everybody, and then you have a private one, and usually you append it such that, for example, if I made a product, I can boot it both on my internal corporate boot trust, but also I can boot it on generic servers which don't have my private CA enrolled, for example.
If your IT department wants to run their own CA, they can just add a second signature instead of.
Yeah, but having ability to append signatures, reorder signatures, remove signatures is needed. Also, like trust buffs as well. Like if you look at Windows boot chains, for example, quite a few certificates, there is a chain such that each signature embeds a signing certificate as well, and then a CA cert, such that you're not validating directly that something was signed by a specific key, but you verify the whole chain. That is also very useful because, like, for example, Canonical, we ship a CA inside our shim, and then we rotate online keys without having to re-sign our shim or re-sign Grub and etc. So having ability to do chain also helps, but I'm not sure how I can embed a cert inside PKSS7 such that later I verify it with a CA.
Okay. Yeah. PKSS7 is flexible enough to do that. Any existing signing tool is not currently flexible enough to do that. So that I'm very glad that we had this conversation because that's not something I would have thought about. We will have to go away and think about that and get back in touch with you. I have very limited time. I just want to say the stuff for signing Grub with an appended signature ELF note, such as it is, which supports being signed by one key only, I have posted to the list. And the verifying Linux from Grub, you can watch the demos. We've got it working, etc. Thank you all, and thank you, Daniel.
Okay, thank you, Daniel, for nice presentation. I think that it will be heated discussion on Grub Devel, or even in our chat, first of all. So once again, thank you, Daniel, for the presentation. Especially as I know it is very late for you, so thanks a lot once again.
Midnight and 32 minutes. It's done.
Yeah, thanks a lot.
Thank you.
Okay, so I think that in 2 minutes we will have next presentation.
Yeah. One more thing from my side. This presentation is available for download right now. So anybody could just press these buttons and use the slides to just download.
Daniel, you're muted.
Yeah, I know. Thanks.
Hi, this is Harry. Do I need to re-log in again to be able to present, or can I just stay in the session?
You will get presenter rights assigned by Benihal. So just wait a second. I think that he should assign. So our next presenter is Harry. He will be presenting system firmware and device firmware updates using UEFI capsules. So just wait a second for his presentation. And Harry, you should get presenter rights right now. Did you get it? Oops, not yet.
There we go.
Okay. So over to you, Harry.
Yeah. Yes, and the download button is in the left down corner of the presentation.
Okay. Let's see, I got to rearrange my screens here. Sorry about that. Close some of these other things. Can everybody see the presentation now?
We can see your desktop, I think.
Okay.
Yeah, you have shared your screen. I already did display your presentation, so you just needed to switch the slides at your need.
So I don't need to share then, or?
No.
You may just turn off the sharing, and now everybody should see the slides as it looks right now.
Okay, great, thanks.
You can continue.
Okay, great. My name is Harry Schoen. I'm from Intel Corporation. I also have asked Vincent Zimmer to be on the call as well to help out with any questions and that sort of thing, since presenting and answering at the same time might be a lot for me. So I'm from the UEFI, both Vincent Zimmer and I are from the UEFI team. Originally, we presented this, Michael Kinney is one who actually wrote the slide set, and we presented this at the Lenovo Connect in Vancouver, BC back in 2018. And that was the time at which we checked in a lot of the code that we're going to talk about here in the EDK2 Tiano Core project to get the capsule update features into the actual code base for UEFI. So in the Tiano Core EDK2 implementation, we're going to talk about some of the things that we've added in there. And this is an appeal to get some of the plumbing and infrastructure into Linux to be able to do firmware in-band firmware updates into the systems out there. So we would really like to see, as a silicon provider, we'd like to see the firmware get updated in all the systems out in the field. This is precipitated really by Spectre and Meltdown. So inside of that firmware, there's the microcode patch, and we really like to see things like the microcode patch and firmware get updated out in the field. So after systems leaves the factory, we'd really like to see systems have the plumbing and the capability to be able to go out there and update their firmware. So aside from the main system firmware and the main flash part, there's also the firmware in the various other devices on the board. Your video card may have a GOP driver. There could be Wi-Fi and Bluetooth firmware in your communications card. In the LAN, there's an ND driver. So there's firmware everywhere around the inside of the board we'd like to see get updated, after the system leaves the factory. And this mechanism is, one of the ways, the standard ways in which you should be able to do that in band. So on the next slide, we're talking about in this presentation how to go to the EDK2 repository and from the code generate a capsule from the DK2 repository, publish it through a service like LVFS, and then distribute the capsule to systems that are out in the field. So using the network, basically having at OS runtime, having a payload, a capsule payload delivered to your system out in the field, and then being able to signal to the firmware you want to be able to do a firmware update through the OS indications bit, and then have it reboot, and then have the firmware process all the capsules, and then flash update the image out in your flash devices out in the field. So that's the general flow of what we're talking about here. It's all in band. We're not talking about BMC or other out of band mechanisms. We're trying to use the main UEFI spec standard and the ACPI standard to be able to get you to update the firmware in your systems. Slide. So in our standard UEFI root process is a standard slide we use to describe when things occur between reset and after the OS boots. In the early SECM PIM phase, that's where you initialize the silicon and provide all the pre-boot silicon initialization. That's where that occurs. That's where a lot of the processing occurs in the firmware to be able to decide whether we're going to do a normal boot or come up and do a capsule update to the system. But normally when we boot up, we just go through the PIM phase, the DXC phase, the BDS phase, which looks at the variables in the system and decides which way to boot, and then come up and boot to your OS. Then we go off and load the Grub 2 or your bootloader, the shim and the bootloader, then come up, and then the next kernel takes over, and we're in the runtime space that a system normally does. So this is just to show you the phases of boot and OS runtime. So the stuff after the transient system load is the point at which we transition over at execute services, and then the OS is then running. So a service like LVFS or some other service from your OEM provider would then at OS runtime be able to provide the service of delivering your capsule payload to your system at OS runtime, and be able to provide the capsule payload so you can then reboot, signal to the system that you want to do a capsule update, and then come around and reflash your system. So here we're talking about the different stages in which a capsule update occurs. So I just described the normal boot sequence, which we go through the normal UEFI post basically, and then come up and then receive a capsule. So so typically you would go run an application up at OS runtime, and in red there after the OS boots, you'd go run the LVFS application, FWPD or something like that, and then you would go up and have it deliver the capsule to your system at OS runtime. Then there's a bit in a variable called OS indications that we can set, and when you issue the reset to UEFI at OS runtime, then you can signal to the firmware that you would like to do a capsule update to the system. Then you would call capsule update at OS runtime, and then the next time when the system comes around and boots in the boot on flash update on the third row there, then the firmware would now understand after we go back to reset that there's a bunch of capsule payloads in memory that we need to take a look at, and then coalesce them to figure out which ones we're trying to update, validate their authenticity, checking their signature basically, and then process them, and then decide which ones to go through and update. And then when we finally boot, again, after we do the reset, again, after we reflash and do the reset, then when we come up, back up into the OS, we then update something called the ESRT, the EFI system resource table, and indicate, hey, we have some new GUIDs from some new capsules that were updated in the ESRT database. So this is the process in which we go through to do a capsule update in your system. So were there any questions so far about this process? Okay, so we'll take a look a little bit at some of the data structures in the capsule update. So for UEFI capsule update, if if you go up to EDK2 Tiano core, there is the code up there to be able to create a capsule header. So the BIOS integrator or the system integrator or engineer who's creating these capsules would first have to go through the database and generate the capsule with some Python tools that we put up there. So he would then take his EDK2 base and first create something called an FMP header that he has to go edit and update to put the payload inside of this data structure to be able to have it published in LVFS or somewhere else. So the first thing during this process that we just talked about was we would do a set image so that the system firmware would be able to pick up the new update driver inside of the system to take the capsule, be able to apply it to the firmware in the system. In that early PM phase, when we're putting the system firmware after that reset is going to go through and authenticate, which they would go through and check the auth info and the payload header and make sure that the system firmware is supposed to apply to the particular capsule that you're handing the firmware to make sure that it is from the correct source, and then the GUID type is something that applies to this particular system. And then once the firmware has validated all that in firmware, there's some other conditions that we have for things like power or battery, or that the system firmware person can put into place to make sure we're supposed to do it's the right time to do a capsule update, basically. Then it'll go ahead and do the flash update of the actual flash part in the system. So once we go through and figure out the capsules we need to update, then we'll go through and actually run the driver that is in the FMP protocol for your particular flash part or system board, and then run that code to be able to actually be able to apply the writing of the flash on the system and apply that update. And then once we finish applying the update, then we update the ESRT table with the GUID of the particular capsule that was updated. In this case, it was GUID A, and then we publish that in the ESRT table so that both the pre-boot system and then, of course, the Linux or the OS system now knows that this capsule has been applied to the system. So back in 2018, in the EDK2 stable tag, we had a number of new features checked into the code base. One of the things Kenny and the team had done was gotten the generation of the capsules to be written in a standalone Python script, so you don't need to crawl into all the little details of building an EDK2 build. So having a standalone Python script made life a little bit easier to generate capsules or multiple capsules. One of the things we changed at that time was up until then, most of the capsules being shipped by OEMs and things like that was a monolithic image. It had both the main system BIOS plus the ME together for the main flash part. So we started concentrating on breaking up the capsules into components. So if the OEM or BIOS integrator decided to break apart the BIOS into separate components, like for example the microcode separated from the crypto lib and the main system BIOS, then we can now support multiple components, have separate capsules if the BIOS integrator chose to break apart the BIOS into separate components and be able to update them independently of each other. So you don't just get one monolithic gigantic flash image, basically. So having different firmware volumes and having the BIOS integrator reorganize the flash part, we now be able to issue capsules for different components in the system. So we brought that capability in back in the EDK2 stable bag tag in August of 2018. We have the ability also at that time to check in. At that check-in, we also added the capability of having multiple BKCS7 keys signed onto the capsule payload. So the ability to process and handle more than one key for multiple images, or like I said, breaking up the firmware volume or the capsules, the flash images into multiple components. That capability was then added at that time. And there's also the pre-check conditions in the firmware. So if you're on a mobile system, you want to make sure before you do the capsule update, there's a capability of adding some code to check the battery power status. You know, if the thermal conditions are okay, we're not in overheat mode or something hasn't been tripped. And if there's any other system conditions you want to put, the firmware integrator wants to put into the system so that you don't do a flash in a precarious state for the system. And then we also added a user interface so that the end user can actually see that there's on the reboot that there's a capsule update being applied. So if you're in the GOP or text mode, you should be able to see some progress bars for each of the capsules being updated, provided there is system code to display that. This also relies on, you can pass this through Linux, some ACPI reserved memory that is being used to pass those bitmap images or whatever images you like to use for a capsule update to indicate to the user something is going on. And then there's some alterations for the FMP DXC module so that we can use separate data libraries out from the main MD module and the other large libs that are already in EDK2 core to break that out for just the firmware management protocol by itself to sort of limit the amount of libraries you had to pull in for that. And we had the test key detection and watchdog detection that was added and built in, as well as the ESRT driver was separated out for FMP protocols, so we don't have to carry other libraries and images for the capsule update. So I wanted to talk about I think back in Lenovo Connect, we had a demo on a Miniboard Max, one of the open platforms we were using at that time to demonstrate this feature, where we showed an update from, they signed a capsule image or 3 images from for this demo where we went through and McKinney displayed getting a Miniboard Max to update 3 capsules basically on the system. So the display update progress lib instance has code in the firmware base, so you can go off and accept images from the outside basically to be able to indicate that there's a progress bar going on while a capsule update is actually being applied or flashed into the system on reboot. So you can display a system logo and then have a general user experience that is customized for your geo in whatever language the system is being deployed in to show that there's some progress going on and send a message saying, hey, please don't pull the power or reset the system while I'm doing the flash update to the system. So give the end user some nice indications not to go pull the plug or do anything drastic to the system while we're doing the flash update. And then for the next set of slides are for if you're actually constructing, you're the BIOS integrator, or you're actually trying to construct the actual FMP module where you're putting all of your update code for the capsules in there. So some of these details are probably for this crowd, not that necessary, but there's a lot of details in here about the ability to add PCD settings and other things to be able to get the device firmware vendor or platform vendor to put in the code necessary to do this capsule update. So I did want to leave some time for some questions here. I know I'm running up here against my time limit here, so I just want to make sure that you know, if you have any questions, we can cover those. Okay. So some of the data structures that Mike Kinnean went through was to go through and describe inside the FMP DXC module configuration the things that you need to fill in basically to construct a capsule image basically. So there's typically an ESRT GUID value for the actual capsule, and that's something that in your database of capsules out there you would need to make sure that you have defined clearly and uniquely for your capsule. There's some other string information that you'd want to see filled in so you can identify which capsule is out there for you to be able to update. And there's some other build time values that we have in there to be able to describe the thing. The other thing is, of course, you need to sign and make sure you have a signature on your capsule update so that you can the BIOS, the firmware can then authenticate and make sure that the capsule should be applied to the system and it's coming from a known trusted source. And then this is the library, as I mentioned before, we talked about the feature that allows you to check to see if the system is in a good state before we reflash. These are the items you should fill in. We have some particular checks that you can do in the system that you might want to fill in to make sure before you do the capsule update. And this was geared toward clients, so check the battery thermal and some other things before you go off and do the capsule update or flash update of the system to make sure it's safe. So you can fill in whatever you want in this library. If you're a server or something like that, you can put other conditions that you need in checking your firmware before you update. In the FMP device lib API, this is where the actual protocols and code is where you need to update. And it's really the second to last item. The set image is where most of the work is done for your particular flash part on your system. So you need to include the code as a BIOS writer or a third-party option writer to include a driver to actually be able to update the flash in your system. So the particular GPIOs and whatever code you need to be able to update the flash in your system, this is where that code goes. And of course, you need to fill in all the data structures to make sure that the attributes for your capsule update are correctly described to the system. So there's a couple of different schemes we have for signing and attributing your particular capsules. So I think Kenny gave three different examples here. The first example is if we had divided up the flash into 4 different components, and here we have 2 of the capsules being signed by one particular key, and then the other 2 drivers signed by 2 public keys. So GUID C and GUID D has 2 different keys signed for those capsules in this particular scheme. So in this case, it's not a monolithic image. Obviously, we have multiple components we're trying to update, and there are 4 different drivers that we're updating. 2 signed with 1 key, and the other 2 signed with each of their own key. So in this particular case, the system firmware needs to be able to accept all these different keys to be able to allow the update to occur. And then when we finish, the ESRT table should then reflect the 4 different capsules that were updated in the system. Okay, looks like my time is up, and we should go ahead and move on, I guess, to either Q&A or move on to the next session.
We can spend 1 minute for any questions, if there are any.
Yes, because the next presentation is a break one, so we may take 1 minute more.
Okay, I just want to make sure if there were any questions, we could go through and take care of them.
Okay, thank you, Harry, for presenting this for us. And we'll start, just to be sure, 8:10 Pacific time. And this will be a presentation about ASI. So see you in 12 minutes. Bye.
Great, thanks.
Yes, and before you go, I will start a poll, and when you will be back, please leave your vote. There should be a ready button. So when you will be back, please press the button at the end of the break, so we will know that everybody is back and we can start the microconference again.
Right, sound check. Can somebody confirm that you can hear me and see me?
Yes, we can hear you and see you.
Great. So do you know, am I getting presenter rights or somebody?
Yes, we will give you the presenter rights when the time for a presentation will come.
But then it will take me, 2 or 3 minutes to set up. So maybe I can get them now.
Not necessary. I am selecting the slides you have sent, and
Okay.
you are just getting the presenter right, and you can start right now, and that's no problem.
All right, sounds good.
You are now unmuted.
Maybe we can get the slides now.
Okay.
Okay, welcome after the break. So next presenter is Ophir,
Yeah.
and he will be talking about ASI for us. So over to you, Ophir.
Yeah, right. So how is this going to work? Am I going to tell you next slide to go to the next one?
Yeah.
Okay.
You should, in the left bottom
Wait a second.
corner.
We have 13 people out of 30 ready after the break. So I don't think we should start right away.
Wait.
Let's wait 20 seconds and start, I think.
Okay.
Okay, let's start, Ophir.
Great. Okay. Hi, everyone. Thanks for attending. This talk is about address space isolation, which is our effort at Google to address speculative execution attacks. We're definitely not the only one working in this space, pun intended. There's also Oracle and IBM. And this talk is actually a slightly abbreviated talk of what we had yesterday in BOF. So about myself and how I got to deal with speculative execution attacks. So 3 years ago, I was an academic researcher. I wrote a paper with colleagues from Michigan, Belgium, and Israel called Foreshadow. And when we published the paper, we thought we broke this technology by Intel called SGX, Secure Execution Technology. And later on, we realized that actually it's much bigger than breaking SGX. Apparently, we discovered something that Intel later called L1TF that can allow one virtual machine to read memory from another virtual machine. And address space isolation is a way to defeat many of those speculative execution attacks. So as a quick background, speculative attack threat, you probably heard about Meltdown, Spectre, L1TF, Foreshadow, LVI, and so on. And those are microarchitectural attacks. They break architectural boundaries in the sense that user space can read kernel memory, one process can read potentially memory from another process, and the big problem is that a virtual machine can read memory from another virtual machine or from the host. And therefore, they compromise customers' data and also the infrastructure credentials if we have any keys on the host. And the current deployed mitigations are either extremely expensive in terms of performance or they're just incomplete, like they're just best offer. And the idea with address space isolation is to come up with a solution which is both complete and very performant. And just to illustrate the threat, if we have two VMs or two guests running on the same machine, guest B, who's malicious, can read memory from guest A, or it can potentially read some credentials or secret keys in the host memory, which is obviously very bad, and this is the attack threat we're trying to prevent. So as a quick refresher, we're going to talk very quickly about L1TF. So this talk is not about speculative attacks, but about mitigations. Here you have some links, at least about my publications on some attacks, if you're interested in more details. But as a quick refresher, here's an image that sort of like says what an attacker can do. If we have two sibling cores on the same physical core, one malicious virtual machine, an attacker virtual machine, can basically scrub the L1 cache. Everything that's in the L1 cache, the attacker can get, and it can either be data that belongs to the VM, to the victim VM, or data that belongs to the hypervisor. And this can be a state that was left there before, or potentially the attacker maybe can call some APIs to kind of like bring into the cache some data. So the question is, why are mitigations so hard? Why are they so slow or so hard to implement? So let's try to understand that. So what can we do to mitigate speculative attacks? So we can stop speculation and put L-fences everywhere, and that's obviously extremely slow. We can try and block the side channels used by these attacks, but that's basically a cat and mouse game. We have you can leak data through the L1D cache, through the L1I cache, through the BTB, branch direction predictor, and so on. It's not even clear if we can stop those side channels in software. Do we have to have hardware mitigations? If we try to stop speculation just after branches, it's also very slow and error prone. And if we try to scrub secrets from the cache, it's also not clear that we can do it efficiently, and when exactly do we need to scrub these secrets. And hyperthreading makes things even worse. If we have two distrusting pieces of software running on the same physical core, one of them can scrub the L1 cache and get secrets. And L1 cache is not the only state that we can have secrets, also in some other microarchitectural buffers that can contain secrets. So what mitigations are deployed today? So first of all, we have to deploy secure core scheduling, basically saying on the same physical core, on the two threads, we have to run VMs that are either the same VM, two vCPUs belonging to the same VM, or at least VMs which belong maybe to the same customer, to make sure that they are trusting each other. But that's not quite enough. What we also need to do is to make sure whenever we switch VMs or switch to the hypervisor, we need to scrub L1 cache. And Intel added an instruction to scrub L1 cache after L1TF became public. And that's very slow, and which means it's expensive with regards to performance. Another thing we need to do is whenever we have a VM exit to the hypervisor, we need to make sure the other sibling core is not running, because if the hypervisor brings secrets into the cache, the other sibling core can try and steal it, but halting the sibling core is also very expensive. So what attack surface is open if we're not constantly stunning cores or flushing L1 cache? The attack surface that's open is basically when we have VM exits to handle interrupts, we may touch secrets, and we want to make sure that we know exactly when secrets are brought into the cache or into otherwise leakable state. So this is the attack surface that we're trying to block with other space isolation. So in order to think about mitigations, we need to kind of like really properly understand the leakage. And there are three basic steps which I think represent all speculative execution attacks. I used to say there are 20-something variants, now there's probably even more. I put a link down here in the presentation to kind of like a more detailed description about the different steps of attacks. But basically, in step one, first, there's some secret being accessed. It can be accessed by legitimate software or by a speculatively executed branch, for example, that brings a secret into a physical register. Then this secret is being placed in some leakable state. The classical leakable state is the L1 data cache, but it can be in other leakable states like the instruction cache and so on. This is the second step, of you can think of it as like transmitting the secret. And the third step is the attacker actually recovering the secret from the leakable state. And the status quo is that the microarchitectural buffers, they always potentially are contaminated with secrets, which can be stolen later on. And the set conclusion is that we either need to stop speculation or continuously scrub state to make sure attackers cannot get secret state from these buffers. And as again, Fauci says, clearly we're out of control because we're not entirely sure when secrets are in the L1 cache or otherwise, and need a better solution than what we have today. So what we actually want is a way to circumscribe, to kind of like know exactly when secrets are in flight. Because if we know exactly when secrets are in flight, maybe we can deploy the expensive mitigations only when secrets are actually in flight, and that we can, scrub the state clean only after we're done dealing with the secrets. And this is exactly what we're trying to do with other space isolation. And the key idea is to use a page fault as a way to differentiate between speculative and non-speculative execution. A speculative execution accidentally touches a secret. If it's not mapped in the virtual memory map, it will not fire a page fault. A page fault will only fire if there was a concrete execution touching a secret. And if we have a page fault, we know, okay, a secret has been touched. Now maybe we need to be very careful with how we handle it. Maybe we want to halt the sibling core now. And the question is also, when do we know that we now need to scrub the state before we resume normal execution? And just to give you like a very simple sense, this is a very trivial example of Spectre version 1. We have the branch here checking that the index is within the bounds of the array, right? And if we look in the middle, we have an access to the array. And if the index is very large, even though we have this if here to making sure the index is within bounds, speculatively, this instruction may execute and touch memory that has a secret in it. And if this memory with a secret is not mapped, what's going to happen, that we're going to get a page fault. So speculative execution will not touch this memory with a secret, but if we actually needed to access memory with a secret, we'll get a page fault, and then we know we need to get into some more secure state. But we still have the question, when exactly is the right time to scrap clean the cache or other buffers that we have? So this is where other space isolation comes into play, and let's try to understand what's going on. So the basic premise is that when we're running a VM, on most VM exits, we mainly touch memory that belongs to the guest anyhow, or other non-sensitive data that belongs to the host. And the idea is that if the guest is trying to steal data, which is technically kernel memory, but it's data that belongs to the guest anyhow, we say, we don't care. You can steal your own data. And the general premise, the general idea is to create different domains of security, and we split the memory into privileged and unprivileged domain. The unprivileged domain only contains data that belongs to the specific guest that's currently running. And if the guest will touch memory which is outside of this domain, we will get a page fault, and then we know we need to do something special. Initially, this domain will only include the kernel space that is relevant to the guest. In the second phase, what we're planning is to actually have this security domain also contain the guest memory and the kernel memory, which is relevant to the guest. So we're going to go over this quickly so we can get to the more interesting stats. Basically, if we have the for loop executing the VM, when we run the IOCTL of kvm run, right before we do the VM enter, we call ASI enter, which in Intel processors will switch the CR3. It's the register pointing to the head of the page table. It will switch it to the unprivileged page table. We run the VM, and later on when we serve the VM exit, if we touch something that we consider to be actually sensitive information, we get a page fault, and then we know to switch the page table. And before we get back into in the next ASI enter, we know that we need to actually scrap the buffers. So what are the challenges? The million-dollar question, or probably even more than $1 million, is what data is okay to place within the unprivileged map? And the general answer is anything that belongs to the guest anyhow, and maybe some kernel maintenance structures which are frequently used, and we don't think they're sensitive. Maybe it's some bitmaps saying which cores are used. Maybe it's some locking structures, which we think that even if a different VM we steal them, it doesn't learn too much about it. Another big challenge that we have is how to handle page faults, which happen within interrupts. If we had a non-maskable interrupt which touch some sensitive memory, how do we deal with the ASI enters and ASI exits? And before we get to some stats from real loads we run, we can also think about this other space isolation as a way to replace kernel page table isolation. KPTI is the status quo mitigation for meltdown. In the same way, we can think about a VM that in most VM exits, it probably just touches data that belongs to the same VM. We can think about system calls in processes. In most system calls, when we need to serve the system call, we typically touch stuff that only belong to this process. So maybe we don't need to switch the page table from user space page table to kernel space page table on every syscall, only when the kernel actually needs to touch something which we consider to be sensitive. But here are some stats we got from experiments we ran, at least from a prototype we started implementing. This is on Redis YCSB. And we can think about the ratio of ASI exits versus VM exits. Let's say we had 1,000 VM exits. How many times out of those VM exits did we actually have a page fault that we had to switch the page table? And what you see here circled in red is basically these ratios. So in this benchmark, we had 2 VMs, each one with 8 cores. And you can see that the ratio kind of like varied between 1% to some higher percentages. We probably actually want to get it somewhere around like 2% or 10%, because whenever we have an ASI exit, we also probably later on need to scrap the L1 cache. But ideally, if we can get those numbers lower, we can actually get really good performance with basically very complete mitigation. And if you can ask yourself, okay, what are those accesses that causes exits? And here's a table, and let's go on over the columns one by one. Like on the left side, the RIP is obviously the instruction address that caused the touch sensitive information. What we have on the second column here is the address of the data. And in the middle column, what we have is actually an interpretation of this instruction pointer. Like what was the source code, the touch data, which is very useful because then we can, like, for example, look at the code and see exactly what it was accessing. And then we can say, OK, it was accessing the task. It was trying to do some accounting about how many cycles are being spent. And we can decide, you know what, how many cycles are being spent? We don't think it's that sensitive. Definitely, if the VM tries to steal its own data about how many cycles it's been using, we'll probably find that. On the next column that we have, when we try to learn what are the ASI exits, it's our best effort estimation about where this memory was allocated. In this example, we can see, OK, the data that was accessed was part of this memory allocation, which was done in the fork function. And then we know that maybe, OK, we can annotate this memory allocation to say, OK, this memory is not really that sensitive. We can actually allow access to that while running a VM. And the next two columns, you can see here on the right are basically the count, like how many events happened. And we can see that this event was the most frequent one. So we probably want to address those accesses one by how often they happen. We can also start looking at memory allocations and see, oh, the most common memory accesses that caused us ASI exits were some per CPU variables. And if you want more details, we can start and look at those accesses to kind of like try and decide, are those accesses really into sensitive data? Or again, we can include them inside the ASI domain to get better performance. And this is really interesting information that allows us to kind of like see if this approach is actually viable. When we run it on various benchmarks, on real loads, we can actually decide if this approach makes sense or not, or what's the performance overhead we anticipate will happen if we try to deploy ASI, address space isolation, on those loads. And to kind of like summarize what we did, first of all, this was a very abbreviated version of this talk. You can check out some recording from yesterday for a more in-depth discussion. But the idea is to kind of like redefine access control of data based on sensitive versus non-sensitive data. While in KPTI, the mitigation for meltdown, typically the access control is based on whether are we in user space or kernel space. In address space isolation, we're trying to say, we don't care as much if we're in kernel space, user space, inside a VM or outside a VM. We mainly care, is this data sensitive or not? And we are trying to do in this approach an allow list approach, unlike a block list. Some approaches suggest, oh, just unmap other guest memory when you're running. And that's definitely useful. But whenever you're using a block list approach, it means you may miss something. And it's sort of like, again, a whack-a-mole game. Like, OK, suddenly 2 months later, some researchers come up and say, OK, you unmapped the guest memory, but you forgot about this piece of memory that also contains sensitive information. Or you unmapped the guest memory, but guess what? There are some host asymmetric keys that were accidentally loaded into the L1 cache, and you need to protect them. So if we use an allow list approach, basically we can kind of like have a discussion on every piece of memory we brought in and have an argument about like, we think it's not sensitive because, and we believe it's a much more safer approach to security. And again, the key idea is to apply the expensive mitigations like L1D flushes only when we actually touch secrets and bring them into the cache. And the idea is to also use ASI to basically replace the KPTI mechanism to have an even more performant mechanism to defeat meltdown attacks. And we're definitely looking forward to work with other collaborators that are working also on address space isolation or variants of it. I think we have 2 minutes, so if anyone has some quick questions, I'd be more than happy to answer. Yeah, as far as I'm happy to answer any questions if we have now. So I think someone here is writing here, this is an interesting but never-ending hunt list of what allow and what to block. So I guess we'll always have the bugs around ASI. So I can tell you what my answer is to that. I think if you do so the thing is, let's say you miss something in the allow list. You don't pay in security, you pay in performance. We believe it's a better approach that if you make a mistake to pay in performance and not pay in security. Because if you forgot about something, okay, your performance went down 1, 2, 3, 4%. That's better than losing your crown jewels. At least that's my take on that. Part of the reason why we're presenting this now in LPC is to basically work together with Oracle and IBM in this space. We definitely need to know that Oracle has been working for a year and a half on something, and we definitely want to take their pieces, and looking forward to also, obviously, push whatever we can provide also upstream. Yes, we are aware. And yeah, Amazon also have a solution. We definitely, the goal is to kind of like merge and have like one good solution that eventually will be pushed upstream.
So I think that is time for last question. Let's wait half more minute. Okay, thank you. I think that there are no more questions. So thank you for doing this presentation for us.
Thank you, guys.
And we have a next presentation in 3 minutes.
Oh. Just checking in.
Sure. Sure. Welcome, Ron.
What do we start in 3 minutes?
Yes, exactly.
Yeah. Okay. What time zone are you in?
We are in Poland, UTC +2.
Okay. Yeah,
So
I'm in California, so I've been.
Oh gosh, this is awful.
I'm not a morning person either.
Yeah, I fully agree. I think that Australia is also is much better than California for now. So sorry about that.
Oh, that's how it goes. That's how it goes. You doing okay?
Yep.
A lot going on this year, right? Crazy year.
Crazy year, yeah. Maybe next year we'll be able to meet. I hope so. We will see.
Yeah. So do you page for it or do I? I guess I use
Yes,
Yes.
you are the presenter, so you have to flip your slides yourself.
Okay, there we go. You know what happened? There was a status display sitting right on top of the arrow to do the motion of the page forward. So,
Okay.
all right, it's working now.
Okay. Let's start in 10 seconds.
10 seconds. Okay.
So welcome to our next presenter, Ronald Nich, and he will be presenting LinuxBoot Ready is Not Ready. So floor is yours.
All right, thank you. Yeah, my name is Ron Minnick. I work at Google. This talk is specifically about what we're learning when we put Linux in Flash and use it for booting, and we call that LinuxBoot. And there is a LinuxBoot activity at the Linux Foundation, which you're welcome to join in. So LinuxBoot, again, is Linux and firmware. This isn't a new idea. This is a picture from 2002, I'm sorry. It was the first Linux BIOS supercomputer that had 100% GPL BIOS. And by that, I mean from power on or reset, we owned everything. We used what was a KExec equivalent called True Kernel Monty back then. So we had Linux and Flash. It turned on the high performance computing network, fetched a Linux kernel over the MirrorNet network, and executed it. And for this, we had to make devices work without BIOS. Fortunately, the only devices we had were memory and a NIC. We had no local disk. That made it a little easier. And so there we are. But as probably everybody knows, the x86 world is no longer at all friendly to 100% GPL BIOS. And in fact, if we look at kind of what the picture is today, this is it, where red is bad. So everything here is red. Red is bad. Red is a binary blob. And all this red stuff finally gets to something like Grub, and then Grub boots Linux, and this could be syslinux or whatever. Down here in the lower left, I'm showing this sort of irreducible minimum binary blob that you'll never get to own called the SEC and the PEI. And that stuff is the kind of thing that turns on memory and that sort of thing. Now, on Zen nowadays, that's actually in a separate ARM processor. But the option does exist to replace some or all of this bad red stuff with nice green open source stuff. And what we've done at Google, and Facebook has done too, and I believe many other hyperscalers are looking at it. And if you can believe it, a car company now uses this on its assembly line. We actually replace some drivers with open source versions. We get rid of a lot of software. You can see what was there and what is there today. And we have a Linux kernel in Flash, and there are Go programs written in Go. This is part of a project called uroot. It does either netboot or local boot, depending. And then eventually we KExec what we call the runtime kernel. So this is rolling out into Google's data centers as I speak. It is in Facebook, a new Facebook switch, and is rolling out at Facebook and many other companies. So this model is happening now. And the key piece in the middle here is KExec. Where do we want to be in another year or two? Well, we kind of want to be here, right? So all the red is gone except for the irreducible stuff that we can't get rid of. And everything is Linux, and the programs are Go. And when we need to, we run a Linux driver to get something started. And then we KExec the runtime kernel. This is where we want to be. We're not there yet. We've done it on a few select machines, but in general, we're at that previous slide where lots of stuff is going. I'll have to talk to Peter Jones' question in a minute. You know, we're all open source. So KExec usually works, but KExec doesn't always work, and we keep finding little things in different select drivers. Many drivers it works like it just perfectly well. But the question is, can your driver start if the BIOS doesn't help it? And some can and some cannot. And more commonly, people are surprised to find the ones that cannot. So here's what I ran into in 1999. The IDE driver came up, kernel booted from Flash, and it said, oh, IDE's been disabled by BIOS. And I thought, well, that's interesting because there is no BIOS. So I don't know how the BIOS could have disabled it. Then when I looked a little deeper, all right, so basically the driver would say, well, if any of the base address registers are 0, then we're disabled. And a key tip here is that not enabled and disabled are not always the same thing. And in this case, they definitely were not the same thing. But you can still find code. I just found some today for the APIC where if a BIOS hadn't explicitly enabled the APIC, the interpretation of that is APIC is disabled, which isn't exactly right. So in 2018, we ran into this little bit in the AHCI driver where there was a test for the version, and the version actually is dragged from a register somewhere in the capability, and it checked that version. Well, no BIOS had ever set it up, so it skipped some important initialization. And the fix from Horizon Computing was to blow away the version check. It really wasn't relevant. And then, you know, we kind of got this thing fixed. But again, this was a case where BIOS hadn't run, and the driver assumed that the BIOS, you know, had done something, or really this code path had never been tested with the BIOS not running, and we had to fix the AHCI driver. And this is the sort of thing you tend to run into when you're doing this. Hang on, waiting for the next page. Or it crashed. Shutdown issues. So this is a core boot ThinkPad X230. We're running a kernel here on the left. We do a kexec and we get the happy result on the right. Now this is not a kernel that was actually going to use graphics. It was just going to continue using the VGA console, but this is what we got anyway. This is kind of a long-standing problem in graphics for anyone who's ever dealt with it, that graphics tends to assume that things are in a happy state, but weirdly, even when they're in a happy state, it gets confused and you end up with this kind of display trash. So another problem is drivers that assume that bus master enable is set. Really, no proper BIOS should ever set bus master enable. That's up to the driver to figure out and set. But I'm discovering that in core boot nowadays, there's a current discussion about how we're going to have to enable bus master enable for a lot of these drivers like NVMe that don't correctly set it up. So this is kind of a common startup problem. Or drivers assume that hardware is pristine. You know, if the hardware is there, it must be in a good, happy place. And in a lot of cases, the people who write this code don't realize how much work the BIOS is doing. And when we remove a UEFI driver, because actually we fix a lot of problems by removing UEFI drivers, occasionally you find a case of a Linux driver that has made some assumptions or missed a few things. You know, it's hard to do because not a lot of people ever get a chance to run on an x86 anymore without all this UEFI stuff having happened. Or they assume that if a register isn't the default value, it has to be good, like interrupt vector numbering. And overall, this is a slightly harder problem than hot plug because hot plug assumes that things are reset, and they probably are reset. But hot plug, you know, is not in a situation where you're dealing with things that are misconfigured. And misconfigured is a tough word because one kernel version's configuration can be another kernel version's misconfiguration. So we recently had a problem where we kexec the newer kernel from an older kernel, and the hardware came up, this NIC hardware, and all the interrupts were off by 10. They were, you know, the kernels had different notions of what the interrupt numbers should be. And the problem was the newer kernel said, well, the interrupts are set up. I don't need to set them up again. This is the way it looks anyway. And interrupts were never delivered. So it's best if drivers don't assume that the non-default state is a good state. And, you know, this gets especially tricky with really complex network interface cards. But as you've seen, even with simple things like AHCI, it can really be easy to fall into a bad situation. But it can work. So I have this lovely board called an Atomic Pi. You may still be able to find them. They were $30 on Amazon, 4-core thing with decent amount of memory, 2 gig. It's a great little x86 card. And I had it run for a week, net booting and net booting payloads. So it would kexec the netboot thing, and the netboot thing would then download and kexec another netboot thing. Worked great until PG&E decided I had enough electrons for the week and cut me off. But you know, it can work. We can run things to kexec things for a very long time. So I could have branded that LinuxBoot ready, except I forgot that I should have tried having it boot different kernel versions as well as just doing a regular old net boot. So I'm pretty sure different kernel versions would have worked because the drivers are fairly simple. It's basically the IGB driver, and I'm not using the NVMe or anything complicated. So I suspect that this could be marked LinuxBoot ready, but I haven't demonstrated it. This is a decades-old problem. So I saw it in 1999. I'm still seeing it today. It's not in every driver. It's just in a select number of drivers. What we're thinking is we would have this marker or name or something that we would call LinuxBoot ready. Maybe we could attach it to the driver in the same way that today we attach it to, we attach the GPL tag to a driver. Maybe it's a config variable. You only select this driver to be used if it's also, it depends on LinuxBoot ready or something. I'm not really sure. I'm not the expert here. I hope some of the experts are in this talk. But the idea is that for any Linux kernel 5.8 or later, the driver shuts down correctly, restarts correctly, doesn't require BIOS intervention, and this third one is key. It has to work even if we don't have the DXE running each time that driver is each time we do a boot. So now in Chromebook, basically to verify suspend resume cycles. Laura, that's a really good point. I wasn't aware of that. In Chromebook, we would require that you do 100,000 suspend resume cycles before we would say that you'd successfully suspend resume. If you got to 99,998 and failed, it counted as a failure. That led to a lot of difficult days when you did get to 99,998. But maybe we could just say, if we can do 100,000 KXX cycles with no failure to boot, no reset to BIOS, no growth in memory footprint, we wouldn't have a situation where the driver, when it started up, I don't know, created a new E820 reserved area that then got passed on to the next KExec. I don't think that happens, but it's a little bit of concern. Performance degradation. We saw a case with a Facebook node where without a certain DXE running, PCIe bifurcation wasn't quite set up right. We fixed that in the kernel, but this kind of thing happens. And then finally, it has to be across different kernel versions. That might be the certification. We already know it will require driver changes in some cases. Does it require PCI change? I've got no idea. Is there hardware that may never work? Yeah, I think we might find there'd be some hardware that it simply would never be LinuxBoot ready. And then finally, it'd be nice to have a way to mark them as LinuxBoot ready. And hopefully, once we have this kind of thing in place, competitive pressure would do the rest. No company would want to be shipping, I hope, hardware and drivers that are not LinuxBoot ready. So that's the proposal. Mainly, I wanted to hear from all of you, so I'm going to try and stop talking and listen. I will quick address some of the comments. I don't think the BDS is more of a binary blob, Peter Jones, than Grub is. But if you go back to that picture, and I can go back if you want me to, Grub is no longer in the picture anymore for LinuxBoot machines. We go right from Linux to Linux, so it's almost not an issue. Laura Abbott, thanks for the comment there on the test driver remove. I think I need to learn more about what that meant. Michael Machinowski, common mistakes. We should, you know what, we need to, as part of this thing, I need to start making that list of common mistakes. That's a very, very good point. Oh, yeah, but Peter, the dark, you're right. Point taken. I think that most people, though, in my experience, view BDS as red just because most people are incapable, me included in general, of building a new BDS, whereas, and also a lot of third-party IBVs tend to ship BDS with proprietary changes and you really can't rebuild it, whereas in general, I will be able to rebuild Grub. Let's see, Dimitri, this is for x86, ARMS, anything, ARM64 and RISC-V, because companies are deploying ARM64 with LinuxBoot today, and it's worked on RISC-V for a couple of years. Daniel, totally true. Yeah, I know about Petit Boot. We've been talking to IBM for years. I would say that we did look at Petit Boot years ago and decided we preferred that kind of thing be written in Go, not C. So we use a Go-based userland for LinuxBoot. It is for local boot too. Actually, ARM is creating a new standard called LBBR, which stands for LinuxBoot Baseboard Ready. And but at the same time, we are working to make sure that LinuxBoot and eBBR will play nice. Yeah, Grant, totally right. It's good to see you here, Grant. Thank you. Core boot. LinuxBoot actually is a payload for core boot. I'm sorry, how many minutes left? I missed it.
5 minutes.
Right, okay, good. I'm running a stopwatch here, and it agrees with you. So LinuxBoot actually began as a payload for core boot, and then when the flash parts got too small, we dropped it out. That was like 2003, 2004. Thanks to UEFI, the flash parts had to be huge, and that made room again to have Linux as a payload and core boot. So actually, LinuxBoot and core boot play together very well indeed.
I have a question.
Yeah, hi.
Can you hear me?
Yeah.
Okay, I have a question. My understanding is that at this point, LinuxBoot is mostly targeted at server platforms. So you don't need, in general, to edit command line or something like that, like you are able to do that in the Grub. So how do you expose the boot menu? For example, if you want to provide LinuxBoot for workstations, do you write the Grub interface, or how would you like to do that?
We have actually. So we do expose the boot menu because we can parse the config files for Grub and SysLinux and things, and it is a very, very, I like crude things, right? It's just a simple textual thing, and you type boot, you literally type boot, and in a fraction of a second, you're seeing all the possible options for what device and what particular thing in the boot config that you want to boot. So it is true that we mostly have targeted server, but even in a data center, sometimes we need to do an interactive boot. So that actually exists now. Yeah,
go ahead.
Sorry.
Go ahead.
Oh,
I had a question.
Yeah.
So you were talking about drivers needing to shut down or put them in the way they were during power on when they shut down the device. But sometimes it could depend on how the hardware is integrated into the system. The power on reset step might be different, or reset state.
Yeah.
So each driver is supposed to know which system it's running on and put it in the right state. That seems like something that won't scale.
It might not. I mean, and I'm not sure I completely get the question, but if you want to catch up with me and tell me more about this, I'd like to hear your thoughts. But I do think that I will say that it will scale for some things because it has to, because we're rolling it out. And so one way or another, we're going to make this work for the devices. Google will make this work, say, for our NICs and for the hardware we use in our platforms. And so I guess the proposal here is to have LinuxBoot Ready be a way we indicate that, you know, a given piece of hardware is going to work. And I don't think we're ever going to get to universality. I would be surprised, but I would certainly like to get to the reasonable subset. Does that answer your question, or am I just avoiding it?
I think it does, kind of, yeah.
Okay.
I can chat with you. I'll go to the chat rooms for this.
Okay, that'd be great. Let me
Go
ahead.
One more question. I have a question. Do you think that LinuxBoot will be in the future, or will be far future, a good replacement for the Grub bootloader or something like that?
It already is for a lot of people, and I think it's going to be becoming more and more common because it always gets back to the same thing. How many times do you want to write the driver for a piece of hardware, right? And if you can write it once, that's better than writing it 3 or 4 times. So I just think it's kind of an unavoidable good thing to have.
Okay.
It was started 20 years ago and it holds today, you know. All right.
Can I offer a counterpoint on that one?
Sure.
With regard, it depends on which market you're looking at. If you're looking at the vertically integrated, I completely agree with you. When you're talking about the horizontally integrated, it's a different set of economics that are running there. And completely agree with that. It's great to write it once in Linux. But if the cost is, and this goes back to my earlier point, if the cost is that the interface is different, it's going to be really hard to get the OS ecosystem on board. So I think what is going to be a much bigger driver for adoption is if the distros and the OS vendors don't have to implement something new.
Yeah.
They still need that same boot interface. They still need to be able to do the shim to Grub and onward.
I think there's a lot of truth in what you're saying. I think we're probably never going to, well, we're going to know how this works out in a couple of years. And I realize I'm out of time. So I appreciate everyone who showed up, and have a great rest of your conference.
Okay, thanks a lot, Ron, for the presentation. I'll join the chat. We have a link to the chat. And if you want to ask more questions, you can do that there. And we'll have next presentation in 4 minutes. Thanks a lot, African.
Okay.
Testing on.
Hey, Greg.
Hey, Lenny.
So who's gonna be talking first?
This is Doug. I'll probably kick off, and then we'll be passing back and forth.
Okay.
So we can start in halfway. Okay, let's start. Doug and Lenny will be presenting right now native booting using NVMe over Ethernet fabrics. So over to you guys.
Awesome. Yeah, hey, this is Doug Farley. I'm with Dell, and I've got with me Lenny Subovitz. And I'm sorry, Lenny, I'm going to butcher your name forever and ever. Today, we really want to talk about NVMe over fabrics and the native boot capability from Ethernet. Today NVMe does not have that capability defined, and we want to really introduce a joint model here and get some feedback on it while this thing is being designed for future standardization. And to do that, we've got a multi-vendor group that's gotten together to build this implementation. The underlying design that we're proposing here is really implementation and protocol independent, but really for simplicity and expediency, we're really focusing on a UEFI and an NVMe over fabrics over TCP as our primary reference implementation here. We'll start with a short overview of NVMe over fabrics and then kind of get into the design direction. There's a whole bunch of acronym soup in here. I'm going to really try hard not to hit you with it, but if you need it, it's in the deck. Please go use it when you're lost. Talking about NVMe over fabrics in general, NVMe over fabrics TCP is intended to be a NVMe over fabrics messaging format on TCP/IP that allows remote NVMe access across the memory fabric, very similar to what iSCSI does today for SCSI. From a NVMe over fabric perspective, PCI bus scanning has been replaced with a discovery service mechanism, very similar to iSCSI's and targets in this sense. NVMe over fabrics has been merged upstream now for a while for both initiator and subsystem target code in the tree. So you can play around with this as you like from a runtime perspective, but that doesn't really cover boot. NVMe itself, to give you some quick orientation of framing, supports multiple memory and messaging type transports. So if you think about NVMe over PCIe with a memory transport, with PRPs or SGLs, those get encapsulated into a payloading structure with a bunch of headers wrapped in TCP/IP as individual payloads and shot over the wire. So when we talk about how do we approach booting from NVMe over fabrics, again, we're really wanting to start with a NVMe over fabrics TCP route on UEFI. This is the simplest thing we could start with. There's no special hardware needed. It's all software. Knock on wood. We want to learn from what iSCSI started with a custom firmware table for NVMe over fabrics, and then for supporting UEFI, we need some device path nodes and other accoutrements to bring this thing along. And then we want to make sure that features in NVMe like discovery log pages are being able to be carried in that table so that the OS is able to recreate this program topology, and this allows you to get to systems that are diskless and be able to boot from network state only. Also, security keys need to be able to exchange through a secure mechanism with the baseband system. We really don't want to stuff them over EF5Rs or somewhere in plain text and ACPI. We just think that's inappropriate. And then some consideration for multipathing has to be accounted for in here because large multipath topologies in NVMe over fabrics are very reasonable and likely. From an ACPI perspective, we're talking about one big table for NVMe over Fabrics features, defined and stubbed in XSDT. It'll be able to contain all the unique entries and capabilities for the adapters, namespace and subsystem attributes, your security context, discovery elements about the exposed subsystem topology from an NVMe over Fabrics perspective. And we intend for all the required and optional features that are really going to be in vogue for connecting to a namespace the first time to be able to be supported inside this table. And specifically in this case, to have support for both boot and non-boot namespaces. We recognize that you need to be able to get to more than just your ESP. You've also got to get to your root partition, potentially other user space partitions and anything else that exists there. And then like we said, all the features that you need for establishing well-formed secure transport need to be available through the structure. From a UEFI perspective, we actually want to kind of keep the device path node simple. We want to be able to give you a unique reference to the subsystem identifier, the sub-NQN, for that NVMe over Fabrics connection, and the globally unique namespace ID, the NID, that represents that namespace uniquely in the global context. And then everything else really needs to get out of the way and be over in the NBFT. You'll be able to do lookups from using that tuple of the NQN and the NID to be able to reference everything in the NBFT. But ideally, the device path, will give you that syntactic sugar to give you your graph topology. Lenny, did
okay. All right, Doug, I don't quite see a way to move the slide, so I think you might have to just
I can do it. Yep.
Okay. All right, so now looking at the Linux sort of boot flow, what sort of impact this would be. So really dividing it into the pre-OS phase, wherever exit boot services is called. Now that could be in the bootloader, it could be in the kernel, really doesn't matter. That's really the boundary line. So before exit boot services, the firmware has already established is a whole stack, driver stack. We're not in EFI, we're not worried about that. That's already established a connection. Bootloader is just using that. Bottom line, we think, is that there can be no changes necessary to a bootloader like Grub, that it can just continue to use the path that has been established by the firmware. And it relies on sort of agnostic interfaces that don't really know exactly, Grub doesn't know exactly the kind of media that it is booting from. The only exception might be, it might want to display for debug purposes the device path, and there's a new node in the device path, that NVMe OF node in the device path. But other than that, we don't think there's any impact on a bootloader like Grub. Now, this is a Grub-specific look. Not sure about other bootloaders, and certainly would welcome any comments either now or later about other bootloaders and whether or not this assumption about no necessary impact to a bootloader. Okay, I guess we can move on to the next slide. Doug?
Yes, you can do it yourself, Lenny. I have promoted you to on the bottom of the slide, there should be a control arrow.
Oops.
It is in the bottom left corner.
Yeah, I see it. Very good. Thank you. Okay, so now we get to after exit boot services. So at this point, we have the kernel's been loaded by the bootloader, along with its init RAMFS, and the kernel is running using basically a root file system at that point out of the init RAMFS, and it has presumably a kernel command line also supplied by the bootloader from whatever configuration file it used to select that kernel, etc. And the task at that point is to mount the real target root file system, the runtime root file system. And ideally, the NIT-RAM-FS doesn't have any unique state that says exactly what you want, where to find that root file system, that we're counting on somehow automatically discovering it and that your kernel command line might have the UUID for a volume that you're looking for, etc. It's not specific to even a particular device name or a device path, certainly. Okay, so what's happening in parallel is that device discovery is going on, and the kernel is essentially waiting for the right UUID to show up. Okay, and so this is something that new stuff would have to be added to the kernel in order to make this happen. So we have at this point the NBFT, and so we need some kernel component very similar to the way the IBFT is handled that sort of looks at this table and makes those elements of the table available for user space to use, for some sort of a discovery daemon in order to help discover the particular NID and make a connection, because the connection that we had before that the bootloader was using, it's been torn down when exit boot services was run. Okay, so very similar to the way the IBFT is presented in sysfs. That's what our current thinking is, that the NBFT elements would be available there, and that the discovery daemon, which would have to be a new component running in user space, is using that information in order to try to reestablish, it has all the information that it needs in the NBFT, excepting for security information, which we'll get to a little bit later. And it can walk through the NBFT and try to make those connections. Okay, and its goal is basically to get to the root target file system. Now, the NBFT may be big. So one of the thoughts is, which we're interested in getting feedback, is that it might take a while, particularly if there are hundreds of entries in the NBFT, the particular NID that you're looking for may not be the first on the list. So should there be some extra hint? Now, the typical use case is that we're coming from that the root file system is going to be on the same namespace as where Grub came from. So we could get that from looking at the current boot variable. But I don't know if that's a really good choice to be able to sort of have a dependence on boot variables. Maybe there should be something in the NBFT that sort of gives us a hint. So we're certainly interested in feedback on that particular choice that we haven't fully thought through. Okay, next slide. All right, multipath. For the most part, I don't think there's much impact of multipath. So pre-boot, if something fails, the Grub should just fail back to the boot manager, and firmware, which will go and just pick up the next boot variable. The sort of default assumption is that that's going to be another path to the same namespace. And one of the open questions that we haven't fully thought through, again, interested in feedback of sort of when what sort of consistency checks should we have on the contents of the boot variables and the NBFT. The NBFT does have the ability to express the multipath, all the different paths to a particular NID. And we certainly in no way expect Grub to be able to use that, but at which point should that be verified that there's consistency between the two? Okay, so that if there's any failure on a given path, we expect something like a bootloader to just fail. once we get into OS runtime, as I sort of mentioned, the NBFT does have hints in it, or more than hints. It has the multipath information. The OS doesn't have to use that. The current OS runtime drivers and associated daemons already have the ability to do multipath. None of that is, none of that has to change. And in fact, the NBFT is probably not going to be complete as far as it doesn't necessarily have to represent and have entries for every single namespace that the OS might use at runtime. That's sort of a site-specific decision. So that, again, we're interested in any feedback on some of the choices that we have here. As far as relying on the multipath information, are the current approaches for doing multipath with NVMe storage, are those considered adequate, and what people would like to see in the NBFT? Okay, I think Doug.
So some future areas of investigation that we still need to go work out here is what else needs to be done around multipath D to be able to better leverage this content. As we kind of hinted at, there's both discovery content as well as grouping for multipath of those NIDs available to work with. And a big one here is support for secure transport for NVMe over Fabrics, especially with NVMe over Fabrics TCP being a TLS dependent transport right now is still missing, and no one has picked up that work yet. So that's an open. In the chat, there was also some question about could this be enabled without user space? There might be ways to do that. Security might be really challenging without that, without a user space component. Quickly, just going through what an OS runtime would look like. If you're an OS, in the OS context, or you're an installer who's trying to add an NVMe over Fabric endpoint into your next boot flow. As we mentioned before, that there's a redfish mechanism in band that the DMTF has a proposal out for credential exchange today. And so the OS would be able to determine whether or not NVMe over Fabric is supported from a boot perspective, and determine if that redfish mechanism is supported, then be able to make calls through that mechanism to see if populating the NBFT is supported, and then it's just instructing redfish, how to populate host, subsystem, initiator, security parameters that need to be created. You may not have to create them if it's adding another path, for instance, and then from there you can fall back to the traditional EFI var mechanics for creating new boot variables for the boot order, or you could do it through redfish and tell redfish to go do it through its mechanism. And then if there's a local config copy of that data that the OS is maintaining, since the NBFT wouldn't be updated dynamically, the OS would need to go take care of that. But this should be relatively straightforward to be able to bolt on, adding new paths in band while an OS is running through this mechanism. So that's the 20-minute overview of the architectural model that we've been piecing together here. We're really interested if the community is supportive of this approach, or if there's something we're not thinking about. Absolutely feel free to come and reach out and yell at us if you want to talk about it further, or if there's questions. Anything on the chat we've missed?
I think there was a suggestion to potentially look at making the multi-pathness more explicit in the boot variables.
Yeah. Yeah, it's a good point. You know, if we're talking about just the slug itself, you know, aside from the prefix from a device path, the sub-NQN and NID really just point to the namespace object, and that can exist across multiple paths. And then from the discovery table, you'll be able to you know, be able to figure out which paths you care about depending on your interfaces that are programmed. Dimitri, we wish it was magical. A lot of moving parts. Oh.
So I think there are no other questions. Thanks, Doc and Lenny, for your presentation.
Yep,
And,
thanks for having us.
And we have 15 minutes break. So we'll see you in 15 minutes. Thanks, guys.
Hi, this is Ian. Anybody around?
Hi, Ian. What's up?
Hi. Yeah, so I just want to just get everything ready for the next session.
Yeah, I will display the slides when the time comes, and I will give you the presenter rights. So we'll,
Okay, so
you will be able to start right away.
Great. So the idea is that about halfway through, I will then hand over control to Dimitar.
Sure, no
Who'll
problem.
take the second bit. But you know, I'll make that. I'll say that quite clearly. So no worries. Yeah.
Sure.
Right.
Guys, can you hear me?
Perfectly.
Can you hear me?
Yes.
Okay. Okay. So I guess I'll just stay muted, and when Ian mentions me, I just unmute myself, and that's it.
Okay, fine.
Okay, thank you.
Okay. Great. Okay, I'll just drop back onto mute for the moment. And what time do we start? 19:30, is it?
Yeah.
Actually, 35.
35. Okay, I'll just go into mute for about 10 minutes then.
Okay, just. Hello, can you hear me? I have some internet issues. Check one, check one.
Yeah, we can hear you.
We can hear you. Yep.
Okay, I have some lag and internet issues, just heads up.
Okay, no problem. If you have some problems with internet connection, please turn off your camera during presentation.
Already turned off, thank you.
Thanks. That's okay, thanks. So we will start in a minute. Okay, I think that we can slowly start. So this is last part of our session, and this part of session of microphones will be focused on attestation and TXT change boot and other stuff. And first presentation is a ridiculous short intro into device attestation. It will be presented by Dimitri and Alan. So, guys, floor is yours.
Okay. Good evening, everyone from Eastern Europe. Okay, so I'm Ian Oliver. I'm security researcher in Nokia Bell Labs in Finland, and I'll be doing this jointly with Dimitar Tomov of Design First Estonia, although he lives in Bulgaria somewhere. This will be a, well, you can read the title, ridiculously short introduction to device attestation. So let's jump in. Feel free to stop me at any point during the first half before I hand over to Dimitar if you have a quick question. Okay, so what we're basically going to go through is quickly describe what attestation is, the role of the TPM and its job as the root of trust for measurement, how that's done, how this is reported, what we attest, the rules around that. And that's actually quite an interesting point, that it isn't just having a TPM in your system and collecting the results or the measurements from that. It doesn't necessarily give you a trusted system. It doesn't really tell you that much unless you actually know exactly what's inside there, and that's what we're going to tell you in this. And then for the last half of the presentation, I'll hand over to Dimitar, who will actually give an example of this, a limited form of attestation called time attestation, which is a very nice way of actually just checking the uptimes of machines within a, for example, data center. Okay, so attestation is basically the process of checking that something matches what you think it does. So in the case of a PC, for example, this is you go to the device, you ask for some kind of claim that contains information about that device, and then you check the contents of that claim against a set of known good values. So typically this would be done in the remote attestation case by an attestation server or an attestation environment, services, whatever you want to call it. It's typically, if you do this against a TPM, the TPM will provide you a block of data known as a quote, which contains information about the state of the system, how it's booted up, assuming measured boot has been turned on. If you've got features such as TXT, Linux IMA running as well, then you'll get measurements from these. Additionally, it'll also provide you information about how the machine is booted up and so on. This block of information should be signed in some way, and that signature should actually be able to be matched against that machine. That information will be sent then to the attestation server, which will then go through the process of checking that against what you think should actually be there. So that's all attestation is. And it could be as complex as it is with the TPM, which is considered to be somewhat of a gold standard, or it could just be very, very simple. You just go to the machine. Is this the machine at the IP address I expect it is? If you think in some ways a simple network ping is a form of attestation, not a very trustworthy or secure one, admittedly, but it is a form of attestation. So if you do have a TPM inside well, your machine, and here we'll kind of restrict ourselves to the x86 architecture, where the boot mechanism has been reasonably standardized by the TCG. Certainly UEFI has all these features. Core boot can do this as well. LinuxBoot I've yet to see, but I think there was pretty good discussion over in the chat about that. And the various other boot mechanisms that are around can support parts of this. So basically, the process of booting your PC means that you power on. You take the initial code that actually runs on the system is called the core root of trust measurement, and this code then will measure itself and the next section to be measured, which will be the initial part of the BIOS UEFI or whatever firmware is going to run next. These cryptographic measurements are written into particular registers on board the trusted platform module, known as the platform configuration registers. The first register in the x86 standard PCR0, it contains the core root of trust measurement. Broadly, this measurement should have come from a piece of read-only memory. It should never change over the life cycle of that device, or typically shouldn't. It's probably the only measurement that you can guarantee coming right down through the supply chain. Now, the next set of measurements that are taken, we call the static root of trust measurements. These, by standard, are written into PCRs 1 through to 7, or even 8, 9, and 10 on some UEFI systems now. Core boot does this slightly differently. They don't use all the PCRs 1 through to 7 along to 10. They'll just use 1 to 4, 1 to 5, I believe. The static root of trust measurements are cryptographic hashes of the BIOS code, the BIOS configurations, any additional ROMs, assuming if you have devices in the system such as the BMC network card that can actually respond to these particular measurements, or requests for measurements, I should say. Typically, most devices don't. What actually gets measured is actually decided by compile flags set at compile time of the firmware. So, if you go and compile your own firmware, then you can actually set these compile time flags that actually extend out the measuring. So you can get to completely ridiculous standards, such as taking cryptographic hashes of each of the memory chips in each of the sockets. So if you change any of those around, if you just swap around 2 memory chips, then potentially you could change the cryptographic hashes that are written into PCR1. The next set of measurements that are taken on Intel machines with TXT, you have the dynamic root of trust measurement, and I believe the next talk is also going to talk a little bit about this. Using Grub and tboot, this allows for example, Linux kernel to be loaded into memory, the measurements of that taken and then written into the trusted platform module. This obviously then requires some additional features, and Intel provided those through the TXT instruction set, which is effectively a form of sandboxing. Once the measurement cycle is over and you get to the exiting of the boot services, then you hand over to the kernel. If you are running with SE Linux enabled, and in Grub you've told Linux to use the IMA or IMA policies, depending on which way you want to pronounce it, then you'll get cryptographic hashes of the static parts, or at least the monitored parts of your file system, made annuls, those will be written into the trusted platform module, typically in PCRs 10, possibly 14 as well. Now at this stage, once you're up in user land, the way the TPM is designed, it has this notion of locality, which basically controls what can be written into which PCR locations throughout the whole boot mechanism. You have 2 PCRs which are available for general usage, which can be reset or written to depending on how you see fit, and these are 16 and 23. And these are the ones that are typically used, so if you have some measurement of particular files or measurements of particular anything on the device at runtime. Now, I should also point out that while this is going on, a log should be kept through the ACPI TPM2 tables. And then once you move over to the runtime, once the kernel is running, these tables should be available to the runtime, and typically they are in the security FS file system. So if I remember off the top of my head, syskernel security FS TPM0 BIOS binary boot measurements is the file to look at. And if you're using a toolkit, for example, like the TPM2 tools, then there are utilities for actually going to read this. So you can actually go and see the log of what was actually measured during the boot process. So there are lots of ways this actually happens and what gets measured, and this will depend on many things such as how your firmware is configured, what compile options were set when the firmware was compiled, and so on, and how you've set up the BIOS. There is a minimal standard, so it is possible to, for example, change things in the BIOS and not see any changes in PCR, say 2 and 3 for the configuration of the BIOS. But this just basically means those values weren't being monitored during the cryptographic process. There is another way of getting information out of these things. So the trusted platform module, this TPM2, provides a mechanism called quoting, and this returns a structure called the TPMS attest. And this structure actually contains information about what was in the PCRs, plus some additional metadata, and it is also then signed with a key that is unique to that TPM. So if you extract the TPM's attestation public key, then you have a way of actually verifying the signature of the data that's coming out of this device. You can also match the PCRs against the ACPI tables as well. So if you manually construct the digests of the PCRs from the ACPI tables, you can match those with what's coming out with what's coming out to the TPM. So you have a number of points of cross-referencing. Go to the next slide. Now, this actually should fit into a much larger scheme of things. So just having a single machine with the TPM, you probably don't need that much of a remote attestation mechanism. In fact, it might not be, you might not need to use anything more than, say, use the TOTP protocol with our utilities to pull out hashes or digests from the TPM and match that against known good values and so on. But if you integrate this in with your supply chain and provenance processes, manufacturers, OEMs, the provision systems vendors, customers can also add their own information into the TPM. The TPM is actually set up so it has a number of hierarchies in which you can place keys, seal NVRAM areas, etc., etc. So you could have a pre-provisioned TPM. So if you're a manufacturer of some interesting equipment, you might actually want to put your own public keys, your own private keys inside there for signing and using the remote attestation process. Typically, one example of this is to place in the endorsement key certificate into the TPM. And this then can be checked with a certificate from the TPM manufacturer itself. So if you get a TPM, say, from Infineon, you can generate the endorsement certificate within the TPM, or actually find it already preloaded into one of the NVRAM areas. You can then check that against the certificate from Infineon, and this will tell you whether it's a genuine TPM from Infineon or not. Other manufacturers have similar mechanisms. TPM 1.2, the previous version really came from a single machine world. TPM 2.0 has this quoting facility that allows remote attestation. Now, while remote attestation of, say, a large number of devices will tell you whether these things have booted in a correct way, or at least they're in some kind of trusted state. Where remote attestation gets very interesting is when you start linking it with, say, your other management and operations. So, for example, in a cloud environment, you may define levels of assurance of different pieces of physical machinery based upon the reports that you're getting from those machines, TPMs. Once the remote attestation has that information, you can then pass that information, say, to the management and operations of your cloud environment and use that in obscure things such as workload management, or you could pass this information over to SDN and so on for further slicing or whatever facilities you want there. So you shouldn't look at TPM and remote attestation as two individual parts, but they actually fit in with a much, much larger ecosystem from where you get the known good values, keys, etc., etc. Now you see on the right-hand slide, part of this slide, there's a piece of text. I'll just jump to the next slide, which will actually show you what's inside here. So this was actually generated from a TPM on one of our Raspberry Pis. Yes, they are not trustable machines in that sense, but you can certainly put a TPM on them, and of course you can have some limited form of measured boot process on them. So what I actually did with here was I selected a number of PCR registers. By standard, there are two banks, a SHA-1 bank and a SHA-256 bank of 24 registers. I selected some of these, so there are semantics to these registers defined by the TCG. But anyway, I selected some of these. I signed it with the attestation key of the TPM and let the TPM generate a quote. Now the TPMS attester structure, of course, is just a binary blob. The Intel TPM2 tools provide a very useful utility called TPM2 print, where you can actually pass in this piece of binary, and then this is the information that you get out. So contained within here, there's a few, let's say, boring fields. Magic and type, these are basically type fields that tell you what type of object this is. Magic is a piece of information that's defined by the TCG. The type 8018 says it's a TPMS attest structure. The next line you see is the qualified signer. So this is the name of the key that signed this blob of data. So if I showed you the signature, when I verify the signature of this, the key that signed that signature should have the same name as the qualified signer. If it doesn't, then obviously you've got something very, very interesting and weird is going on. So you have this cross-check between the signature and the actual data being signed. Extra data, this field is actually blank here, but you are allowed to pass in information into the quoting mechanism, and this is typically used for nonce to protect yourself against replay attacks. It's a free form field. You can push whatever binary data you want inside there. Obviously, you don't want to pass in too much. The TPM is a fairly limited device anyway. The next section of information called clock info. The TPM has its own internal clock and a number of counters. The figures actually shown here are slightly crazy, as you'll see. I have not made 36 billion or 360 or 3.6 billion resets of the TPM. The clock counter on board the TPM, this is an independent clock, and it runs, I think it's got a life cycle of maybe 4 to 10 years, depending upon the manufacturer. This is independent of any other clock, and it just tells you how long the TPM has actually been powered on. If you ever see this clock go backwards or not increment between quotes, then you know that something very strange is going on. Either the TPM has failed or somebody is trying to fake something along the lines. Reset count and restart count are counters that are incremented on power cycles of the TPM. So reset count is basically the number of times the TPM has been power cycled, which corresponds to the number of power cycles of the device that it's on. So if you power off the device, then this reset counter will increment by 1 on the next restart. Restart count refers to the number of suspensions, and this will really depend upon the architecture that's underneath. It should be suspension or hibernation. on an x86, but Intel Management Engine, we've noticed on some of our devices, tends to get in the way. Safer actually talks about how the device was powered off and whether it was powered off in a clean way. Firmware version, TPMs have their own firmware on board, and this is the version of that can be checked against the manufacturer. The next section, the only really interesting field here from the quote is the PCR digest, and this is a SHA-256 or SHA-1 of all the hashes that you have just selected during this quoting process, and it's that PCR digest that you will actually go and pass then to your attestation server for checking against known good values. Right. So when it comes to actually checking this, we can actually break this up into a large number of rules, and the rules that you will apply will depend upon how much checking you want to do. I need to be a bit careful with time here. So the first one is quite simply, is this a quote structure? Does the magic and type fields match? Not an interesting check per se, but it is one that has to be done. Is the quote signed? Does the name of the signer match the qualified signer? Nonce, etc. Does the attested value match the known good value? These are all kind of normal things that you can get out of the quote. But where the quoting gets interesting is when you start looking at quotes taken over time. So if we look at the history or the assurance of the quotes, has the device quote changed in any way since the last quote? Some fields should change, some fields shouldn't. What properties in here should have changed? So if you run an update against the system, then you should very well see things change. If you're not seeing that, then those updates haven't been pushed out. If the hashes don't match known good values after an update, that's an issue. I'll hand over to Dimitar in about 1 minute. And then, of course, taking attestation over time. So, have I gone too far?
The 1 minute warning is for the whole talk.
Okay, Dimitar, run for 1 minute, please.
Yeah.
So Dimitar will now give a quick demonstration of this.
Okay. So everything Ian explained is very nice and well, but it's complex. There is one thing that the TPM can be used, and I have not seen to be used widely, and that's time attestation. Why this is so special? What is the motivation behind it? Because the TPM itself is the root of trust for reporting, which makes it unique. At the same time, the time, as Ian explained, the clock is internal. It's hardware. The chip itself is tamper-proofed, physically tamper-proofed. So this is, in a sense, the hardware clock that you really want to trust. And because we are testing data that's internal to the TPM, that makes it unique in a sense. So the idea is, and I'm really running here, is to have periodic attestation of your infrastructure, of your user stations, and to base that on the TPM time. Again, very quickly. So when we do a quote with the PCRs, the state of the system, someone needs to feed the data. Someone needs to feed the data. Ian, could you please mute? Thank you. Someone needs to feed the data to the PCR, and we also need to calculate hash and then to do a PCR extend operation. The PCR extend operation is a cryptographic operation that does not lose the existing information in the PCR, but appends the new one. But someone needs to feed it, and that makes a requirement for secure environment, secure application. When we are testing time using the TPM, everything is internal. We are testing the clock of the TPM that's internal to itself, and it is the root of trust for reporting. So that's what makes this use case so unique. I've prepared a really brief overview of all the stacks, and I wanted to talk about my choice of stack, which is a new one. It's the Wolf TPM stack because it can be used in bare metal, but I'll skip that part. Then how to test time. As Ian said, there's a clock inside, and we have 2 values, which are very interesting. So the one is once we do the sign timestamp, which is an example in Wolf TPM that I recently added, it generates a report of the TPM time. And you have just a final sentence. You have 2 very distinct times. The one is the uptime since the last power up, and the other is the total time the TPM has ever been on. So your system could have been reset 10,000 times, and you have the cumulative time, including the reset counts, which is very, very useful. And join the Helsinki conference where I'll be talking more broadly about these topics. And thanks for the opportunity. I'm not hearing you.
Oh, sorry.
Yeah.
Half a minute for questions. Half a minute for questions.
Okay.
So I was going to ask about the time. One of the things that we can do with trusted keys is actually to tie the key to a particular time to make it expire. And unfortunately, the TPM's internal idea of what the time is pretty useless for this. But one of the things we could do on boot up is to sync the TPM's time with the system time, seconds past midnight or whatever, 1970, the usual one. Do you think this would actually be useful for your use case as well? We're not doing it at the moment, but it's one thing we can do.
So I know for sure that there are uses where the TPM time is used to be tied to validity of certificates, and because it's relative. So I make a certificate signing request, and based on the uptime of the TPM, let's say in 10 days, I no longer trust this certificate, I revoke it, or I do something else. One very specific use case of the TPM time, because it's relative. It's not a real-time clock, but I can use it, for example, stuff like time of flight or maintenance periods of IoT and edge devices, which is very nice.
Okay,
for keys, definitely.
Dimitar, Jan, we are out of time. Sorry about that.
Okay, sure.
May I ask you to move your interesting discussion to chat? I think that we can continue there.
Of course.
And thank you for your presentation, Jan and Dimitar. And we have to switch to another presentation. Thanks a lot, guys. And there is a second Daniel presenting. And right now, Daniel Smith will be presenting advanced applications of DTRM with LinuxBoot, a secure launch for Linux. So over to you, Daniel.
All right. Can you hear me? Yeah, there we go.
Yeah.
All right. So I'm going to walk through some advanced applications of how DTRM can be used. In past presentations, I've discussed, how we're going to bring DTRM to the Linux kernel.
Daniel, you are quite quiet. You are quite quiet.
Am I quite quiet?
Yes, we very barely hear you.
Better?
A bit, but not so much.
Not really.
Not much.
Okay. I've turned up the microphone as much as I can, so I apologize. I'll try to speak louder, see if that helps.
Okay. That was.
So, just to reiterate real quick, so the focus today is going to be on just the applications of DTRM, since we've already covered I've covered in past presentations on bringing DTRM to Linux to secure DTRM. So we'll go through a quick introduction. Then we'll go through what's referred to as an early launch case, as well as then late launch cases. Just going to go through a couple of them real quick, and then talk about some future capabilities we're going to be working on, and then we'll move into Q&A. All right, so just real quick as an introduction, here's just the people that are currently contributing to TrenchBoot and the various efforts we have going on underneath that. Getting into where we're at currently with secure launch is the current infrastructure that we needed to be able to pass DTRM related information during the boot phase was merged in 5.5. We did an RFC for the actual secure launch patch set itself that built on top of the current infrastructure. We did that back in March. There is an RFC for a Grub patch set that was sent later in May. And if everything goes well with testing, we should be releasing the actual full patch set to LKML for merge. If you want to see any of our past talks about that, you can see all our past presentations on our project page, which is on the in the project info page slide at the end. All right, so just some common understanding. Launch integrity is something that it's a responsibility the user or the enterprise is entrusting to the system to just make sure everything is the correct items are loaded into memory. The launch integrity itself is often implemented as a load integrity, as this is a very critical thing to understand. And that even though the launch integrity trust chain can actually load multiple things or inherit multiple things into the TCP. So they're not always, everything in the TCP is not necessarily part of your trust chain for your launch integrity. Only the components that did the actual transitive trust is what you're hearing here. And then when it comes to dynamic launch, as I kind of pointed out at the beginning, we actually have two operational models, which is the early launch and the late launch. Early launch is specifically focused on when the system is initially getting powered on. So usually is done in conjunction with the SRTM or the firmware load. And then late launch is actually when you use DRTM after a kernel has taken control of the system and you want to use the dynamic launch capabilities for some use case. So early launch. So there's the classic SRTM supplement that this is what T-boot does. This is what everybody typically thinks of when they think about DRTM. Typically what you're trying to do is you want to reset the root of trust for your launch integrity trust chain. The purpose being is that you want to try to remove the system firmware or possibly the bootloaders or other items that might have ran in between when the original SRTM root of trust was established and when you're actually getting ready to launch this operating system. This is especially useful when your actual root of trust for your firmware was actually not rooted in hardware, i.e. you didn't have a boot guard or an Open Titan chip or DICE or any of these other SPI interposers. The downside to taking these approaches is that you basically have an increase in your boot time. And then since you've now moved to a root of trust for measurement, you now have to have a separate assessment action to ensure that the right components were measured, or the measurements were correct through either a local attestation or a remote attestation mechanism. So just kind of step through it on the right here. So typically what happens is you have the system firmware come up, do any verification and measurements that it might do to call into the bootloader. The bootloader makes the actual DL event, the dynamic launch event, which is a CPU instruction, which causes the CPU to actually measure your dynamic launch environment, which then you can use to measure and execute the target runtime system. So in terms of just the status of where secure launch is for this kind of a use case, this is actually what we referred to as the first launch in some of our other talks, and is the primary focus for the initial implementation and release. And as we said, the Grub patch set is out. The RC patch set's out. We should be releasing the final patch set for Linux. And then as an exemplar, we actually have you can build an instance of uroot that actually can serve for your initramfs in your dynamic launch environment to do any measurement, log preservation, and do the kexec. So to extend the SRTM, the previous one, the SRTM supplement is something I've called Measure Secure Boot. It's something when I started the Trench Boot project, is one of the capabilities I've been wanting to build. Basically, what it does is we are using the DLME to establish a root of trust to then pivot back into the secure boot plumbing that is already inside the Linux kernel. some of the reasons that we want to do this is because, as was recently discovered, the CRL revocation process is actually complicated, and it's a challenge for secure view or secure boot. In cases where you might want to eliminate Microsoft out of the trust chain, when you have OEM devices that make it complicated to do that. I've experienced devices where firmware upgrades basically reset the secure boot keys out from underneath me. And on top of it, the DRTM PCRs tend to be more predictable and less fragile than the SRTM PCRs. So that, in terms of doing forward sealing capabilities, and makes this an easier way to pivot while still keeping your root of trust verification infrastructure. Likewise, it has the same challenges that you have with the SRTM supplement. You increase your boot time, and then you also have to have some RTM that assessment that can basically assess whether the CRTM has the correct measurements. So just to kind of walk through this looks very similar to the SRTM one. The difference is that when you come into the DLME that is getting measured by the CPU, it will also be measuring the hash of the certificate, the public key that you want to use as the verification key for the rest of the secure boot verification chain. On AMD, which is where I was primarily focusing on, this actually is, we can actually put that hash as part of the CRTM measurement itself, as the SK-init instruction works. But for Intel, unfortunately, the ACM is actually what gets put in as the CRTM, so the hash actually winds up, the measurement of that hash actually winds up being later. In terms of implementation, as I stated, this is just an extended version of SRTM supplement. The work in progress, so in the A&D implementation, we have the measure secure boot key hash field planned for in the secure loader header. That way it actually gets measured as the first measurement by the DRTM. In planning for Intel, we're still working out the best place to store and pass the certificate hash. As I stated a moment ago, the earliest we can get it, the better, but we can't make it part of the first measurement, unfortunately. And then finally, the other aspect of it is once we're at that point, we have to have an approach for activating the secure boot infrastructure from the DLME. So via the kexec, we have to have a way of chaining that RTB through. Those were the early launch cases. There's not very many more differences you can do with DRTM in the early launch. It's just more about nuances of what you want to do with those early measurements. In late launch is actually where you get into some more interesting cases. So the first one is the secure upgrade for either firmware or OS. And what the purpose here is that you want to have a controlled and verifiable boundary to move from your unpatched state to a patched state. So what you can now do, and what you're attempting to do here, is that in some systems, machine reboots can be very expensive. So you want to be able to, have kexec across, and you don't want to continue to have kexec with a very long root of trust all the way, chain of trust all the way across that. So this provides a means by which you can basically reroute the chain of trust back into the hardware and then continue on. And then because you are using an upgrade environment, you can enforce that only a valid environment is allowed to do the upgrades of either your system firmware or your Linux system. Some of the challenges here is the overhead that you have within adding an external update service that will basically have to function in terms of attestation validation for the DLME before you allow the upgrades to occur. So This one's pretty straightforward in terms of how the flow goes. You have an existing Linux system. It needs to do an upgrade, whether the user triggers it or an enterprise triggers the upgrade. That boot or the dynamic launch will land you inside of the upgrade environment, which then can communicate with the update service through an attestation to verify that it is in the correct state and retrieve the updates that are going to be applied. Then you can also control that it's allowed to talk to the firmware as well as the Linux system itself. And then when it's done, it will be able to dynamic launch right back into the upgraded system. Your root of trust starts here, and your chain of trust can continue on. And it is, again, just with the early launches, you can just do a RTM chain of trust through this, or you can actually use the measure secure boot and do your root of trust verification trust chain. So for secure launch, this is what we refer to as the relaunch use case. It's the next one to be worked on after the first launch use case has been completed and upstreamed. So right now, really the only major piece for Linux that needs to be done is we need to be able to do a dynamic launch preamble as part of a kexec operation. So another situation you might be in you might want to deal with is secure wake up. You want to verify the integrity of your Linux kernel post sleep. Some of the reasons being is because as soon as you go into a sleep state, the kernel has lost all control of the platform. Somebody can tamper with the platform behind the kernel, and then when it comes back up, it may think that it's really in a pristine environment when it's actually in a tampered environment. So the DL event will actually put your hardware into a known controlled state for you to evaluate everything is back to what it should have been before it shut down or went into a sleep state. One of the biggest challenges here is crafting an assessment action to validate the root of trust chain through to the running Linux system. So in terms of the way the flow goes, typically you'd be in your Linux system, you would enter a sleep state, which would take you down to system firmware, whether that's that's S3 or S4. Wake event fires. There would need to be a wake event dynamic launch shim or stub that knows how to make sure the system is in the right state to make the dynamic launch call into the CPU, and then at that point you are into a traditional startup sequence, which would then bring you through to measure, verify the Linux environment. In terms of secure launch implementation, secure wake up is not really a use case we have on the roadmap at this time. Some may find it appealing, and obviously contributions are welcome. So this might be a case if this is something of specific interest that might meet a need that somebody has. We would be glad to work with them and help integrate their capability. So isolated execution, this last one for dynamic launch. So Flickr was actually a paper done back in 2008 by John McCune. And it actually used DRTM to execute security-sensitive pieces of code outside of the Linux environment to ensure that a tampered Linux environment could not interfere with the security-sensitive execution. So, one of the reasons being is that as I kind of stated here, which is that you want to be able to execute a piece of code without any threat of the kernel or user space. The downside or challenge with this is that it is a dynamic launch is a disruptive event that causes some unexpected state changes, and so re-entering into a running kernel is they did have a solution that worked, but that is a challenge that has to be mitigated. terms of secure launch, specifically what is of interest for us and for me specifically is actually trying to bring about a true kernel runtime integrity solution that could be run in an isolation execution. As I stated, doing a dynamic launch does cause some pause to the system. It can be disruptive. So you want to this would be done at states where you can take a significant pause because you're about to do something very important that you don't want. You want to make sure the system is in a good state before you did it. So in the near term, right now, we're looking at actually bringing this kind of capability to Zen as we bring the dynamic launch capabilities to the Zen hypervisor. But again, here's another situation where if somebody wanted to look at like the LKRG implementation and find a way that can be run inside of a DLME, that would again be very much welcome, and we'd be glad to work with you to get that folded in. Future capability development. So kind of went through some use cases today and just some quick ones, try to fly through them, just give some idea of what you can do beyond just using it as an early launch capability. But to make these capabilities even more useful are things like working with the community to come up with a good database of known good measurements that can be provided and potentially provided as an attestation service. You know, the Linux, the firmware update group, that would be a great collaboration if anybody in that group is willing to work with us on that. As I pointed out, an external runnable runtime integrity capability that actually inspects the runtime and not load time integrity. And then, even a little further down the road and more theoretical is coming up with a cross-vendor virtual dynamic launch instruction defined that hypervisors could implement. There are some rough implementations in it demonstrating sknet and senter, but it would be better to see something more standardized that all hypervisors could implement and guests could leverage. So just some project info if you want to get in contact with us. You can pull down the slides and reach out or join any of our conversations on Slack or our mailing list. And questions.
Let's say we have 1 or 2 minutes for questions. I think that you have 2 questions from James in the chat.
Yeah. So security evaluation of DLME itself. In what sense? You mean doing some static analysis or doing some CNA activities? I'm not for sure what you're referring to there.
Well, pretty much for every transition from a static to a dynamic route, you have to verify the security properties of the dynamic route are not susceptible to faking or interception. So if somebody can attack your system before the transition to DLME, you have an insecure system. And how do you prove that the attack wasn't done? So you presumably evaluate the static root of trust against the list of known certificates and say that that's it. But how do you know that DLME did that evaluation correctly and somebody didn't tamper with it?
Oh, so you're, again, this is why I put this in the preface. So right now we're focused on load time integrity. If somebody tampers with your runtime, that's a runtime integrity issue, and we don't have any runtime integrity issues. This is, again, I think you're picking at the bone that everybody picks at when it comes to dynamic launch, which is if I can compromise SMM, I can therefore I can tamper with your environment after you've done your launch. But at the end of the day, in terms of did it do it right, I mean, that's asking, did the CPU measure the DLME, or well, actually, usually there's a small module, right? So in Intel, the ACM is actually what's measured by the CPU, and AMD, it's a third party can provide what's called a secure loader block that the cascade instruction will measure. And then you make sure that those are all done, they do their measurements appropriately after that. So in the case of the ACM, that's written by Intel, signed by Intel, it's binary blob, there's not much to do. In terms of the secure loader block, it's a third-party implementation, which is what we have in the Trench Boot project called the landing zone that we're working on. And it's open source code, so people can verify exactly how we're doing the measurements and storage. And it's actually still in an early stages, so contributions are definitely welcome in that aspect.
Okay, thanks, Daniel. I think that we are not have a time for more questions. So I ask you to move your discussion to the chat. Thanks a lot, Daniel, for presenting. And we have to move on to other. Thanks a lot, Daniel. And we have move on to the next presentation. It looks that it is last one. It is ours. Okay.
Yes, this is the last one.
Time is passing so quickly.
Yeah, I think no, I cannot enlarge the presentation even more. So welcome to the last presentation of our micro conference, which will be about passing and retrieving information from bootloader and firmware. And mainly I would like to mention a topic of retrieving the TPM event log from the firmware to bootloaders by the operating system. And by that, I don't necessarily mean only the SRTM event log or the BIOS event log, but also the DRTM event log. Short introduction about who I am. I work as a firmware engineer at 3M Embedded Systems Consulting, and I'm a core boot core developer. So I'm a kind of firmware guy, passionate in hardware security and various advanced hardware firmware features. So the problem mainly is that we have various booting methods. For example, we have LinuxBoot, which bases on kexec. We have UEFI firmware and the EFI stub in Linux. We have also the legacy boot solution, etc., etc. Each of these methods can pass different information in various ways. But in terms of capabilities and features, these firmware implementations are quite similar. Either it is UEFI, core boot, or Linux boot. They typically expose or pass the same, or if not similar, information to the operating system. Like we have a standardized ACPI tables, the memory map, etc. Yet there are still problems with how to retrieve this information from firmware and bootloader. So I have encountered a small issue with TPM event log last time, and when I analyzed the topic, I noticed that there are specifications and specifications. For example, let's take the TPM 2.0 event log. We have basically two ways to retrieve it. We have the boot services method that is widely used by Linux kernel for some time, or we may use alternatively a TPM2 ACPI table that points to the address with TPM event log area. Apparently, the latter option is not so valid because the TCG2 EFI protocol get event log API should be used instead of the TPM2 ACPI table to retrieve the TPM 2.0 event log from the UEFI-based firmware. So we have like two sides of one medal. We have a TCG-defined ACPI table, which points to the log area, which could be used to retrieve the log. And on the other side, we have the UEFI specification, which tells us to use the boot services to retrieve the log. And it seems like UEFI is everywhere, and we have to rely on UEFI. But what we don't have UEFI. We may have a LinuxBoot, which is quite common nowadays, or we can have a very common core boot implementation with legacy boot. What to do in such situation? And what is more, the UEFI way is much more troublesome than needed. As we can read in kernel documentation, as I cited below, it is very troublesome to retrieve the log because the call of exit boot services additionally creates another entries in the event log, which need to be retrieved by the Linux later on. So the UEFI creates additional entries of these logs in some table that needs to be parsed later. So in fact, we could just read the TPM event log address from the ACPI table, but we need to bother with these various UEFI issues. But just recently, the support for TPM 2.0 event log retrieving from ACPI has been added to Linux, thanks to the Stefan Berger from IBM. And yes, I wish I had noticed it earlier, so I could save a few days of debugging, workarounding, and stuff. And I think this is a better solution because ACPI tables are much more common and are not specific, for example, to UEFI. And yes, when it comes to DRTM event log, we have a TCG DRTM architecture specification, which kind of gives us the best practices how the event log should look like. But Intel went their own way a little bit with trusted boot implementation, and they put the TXT event log in so-called TXT heap. So it is not generic solution. Tboot also provides their own tools to handle various features of the Tboot. And on the other hand, the DRTM specification says that the event log should be separate from the firmware TPM log. That's true in case of the TXT heap, but there is a lack of unified approach to store these logs from DRTM. So what should be the solution? Again, I think it should be the ACPI. The DRTM event log may be also pointed by DRTM ICPI table, which is defined in the DRTM architecture specification. Besides the TPM event log, it holds also various information about DRTM capabilities, which are supposed to be platform agnostic. So as I mentioned, it can point to the DRTM event log area, and it can be simply retrieved in the same manner as TPM2 event log, and can be populated, of course, in SysFS. Additionally, it creates many more ways for use of these event logs. Like, for example, the earlier mentioned TPM attestation. We can just read out the SysFS file to retrieve the log, parse it, and include it in the TPM quad for attestation. So my question is, what do you think of such solution? Would it be acceptable to get the DRTM ACPI table implementation in Linux kernel or not? And thank you.
So I think the primary reason that the TPM2 event log on UEFI systems is not exposed via ACPI directly was the presumption that you could end up with fairly large event logs. And if the operating system had no need for that logging information, it could simply choose not to copy it from boot services data to runtime data, and therefore the log would be freed afterwards and you get those resources back. In the DRTM case, I can't see any reason why you would do DRTM without wanting the logging. It's sort of the entire point. So from that perspective, using ACPI seems like a completely reasonable solution to expose the table.
I understand the rationale about the UEFI TPM event log, but from another point of view, there was no alternative to retrieve the TPM to event log for such a long time. Yeah, so this commit I have pointed was has landed in the Linux master branch in July this year, so it's quite late.
Right, sorry, my point was more that if you didn't want the DRTM events, then you wouldn't be doing a dynamic launch. So I think using a static table, like using an ACPI table, doesn't have any drawbacks. I think it's a good solution for the DRTM event log.
Yeah, thanks for that feedback. Yes, James?
Problems with the I was going to say the problems with the UEFI one are just that if the system doesn't boot through the UEFI stub, or the bootloader does exit boot services, we've lost the log, which tends to be what happens to a lot of people. But we are getting better at actually getting this all to work. So on most systems I have now, the UEFI event log is preserved. So I'm not sure how much of a problem this is versus how much of a big cock-up we had before with getting exit boot services in the right place.
So when it comes to event logs and ACPI tables, they are created by the firmware. So the firmware is responsible for creating such tables and reserving the space for the logs. In such case, putting it in reserved memory so that it won't be lost during transition from bootloader to the operating system.
Yeah, but Matthew's point was that a lot of operating systems don't care. The operating system doesn't care. We do want to lose the log.
Okay, I see. Okay, so are there any other questions to my part of the presentation? Okay, I guess not. So I will hand to Daniel right now. He will continue this topic. His own concerns about retrieving and passing information from bootloaders to operating system. Here you go, Daniel.
Thanks a lot, Michał. Last Daniel is closing our session. I work for Oracle, and I'm software developer and Grub PowerPC maintainer. And today I would like to discuss how to pass and retrieve the logs from the bootloader. So at the beginning, just a second, how to move on?
Sorry.
Okay.
Sorry, you may continue now.
Yeah. Thanks a lot. So why we first of all some legal statement from my company which is required, and why we need this information from the bootloader. So the idea of the bootloader log originates in TranchBoot project, because we quite quickly realized that we need a lot of information how the platform was configured during TranchBoot startup. But we quickly realized that this functionality can be also used by others, for example, by Firmware, Shin, or other bootloaders. And that is why we try to make it as generic as possible. We started working on and design, and we came up with two structures. One is a simple header which describes the bootloader log, and another one is the structure which contains the message itself and properties of this message. So let's discuss the header. The header contains four main members. The first one is version, which describes the format version of the bootloader log. Right now it is 1. The second member is called producer. It describes the producer or bootloader which produced a given bootloader messages. Initially, we considered this as an integer, but after discussion with Peter Jones, we think that maybe it makes more sense to use it to define it as a null-terminated string. We also have a size member, which is the total size of the log buffer. And we have a next off, which is simply the offset of next available log message slot. And after that, we have an array which contains the messages. The messages are put in a structure which contains the message itself, but it's also described the properties of this message. So there are 3 members which describes properties of this message. 2 of them were borrowed from syslog, and the meaning of level and facility is similar to syslog. So the level will be used to differentiate normal messages from the debug messages, and the facility will be used to describe the source of a given message. We also have a third member, which is called type. It is similar to facility, but it is defined as an array, as a null-terminated string instead of an integer. We decided to do that because some bootloaders may use integers to identify the source of messages, and in case of Grub, for example, we use strings to describe the sources of messages for Grub dprint. The type will be used for only dprint messages. And last array contains the null-terminated string, which is message itself. After discussion, we also got some suggestions that it makes sense to add a timestamp to this structure, and we are going to add this in the second version of, let's call it, spec. How we are going, how the Grub logging works. So the Grub collects the logs messages into temporary buffer, which is dynamically reallocated. And logging is done via calls which are placed in Grub print functions. So this way we are getting most of the messages which are produced by the Grub in quite simple way. Just before passing the control to Linux kernel, the bootloader log is copied to a final resting place. We are using a relocator to allocate this resting place, but since that moment the log cannot be updated. The Grub logging is controlled through 3 variables: Grub log, Grub_log, which is used to enable disable logging, Grub_log_debug. This is similar to debug variable, which can be used to specify which debug messages go to the bootloader log. And the last one variable is used to enable, disable file name and line number logging in case of debug messages. How do we pass this information to the Linux kernel? In case of Linux kernel on BIOS and trench boot, we are using boot params or 0 page. And we just added two members to this structure. One is an address of bootloader log buffer, and another way is a size of bootloader log. In case of UEFI, the situation is a bit different. After the discussion with Peter Jones, we came up with something which is called configuration table. So we just use functionality from UEFI spec to register the configuration table with a specific grid. So bootloader registered the bootloader log as a configuration table, and after that the kernel is looking for this specific table with specific grid in the list of configuration tables. And after that, the kernel exposes the bootloader log through sysfs. Then user space tools are able to pass logs as needed. So currently, the specification of the format of this bootloader log is under discussion, and also the code is a work in progress. The initial version of implementation was prepared by Oracle Inter Alec Brown, and it is posted publicly. The specification also is available publicly. Currently, it is an email thread which was started on LKML and Grub Devel. This is the first version, but I'm going to post in the following weeks the second version, which takes into account all changes proposed by Peter Jones and other guys. And also we have some code which implements the first version of the log buffer. So okay, so we have the Grub patch, which contains the changes needed to the Grub bootloader. This is not a very big thing. The Linux kernel patch, which exposes the bootloader log via sysfs, and SLStat tool, which is ChallengeBoot specific tool, which displays the bootloader log, but it also additionally prints the contents of Intel TXT register. So as I said, all these patches and specifications are available publicly. And right now, I would like to at least ask 2 questions. Is this feature interesting for you? And there will be a poll for it. You can see it. Okay. Okay, it looks that most people are interested in. Some will know. And another question, is there any chance to use it in other cases? There will be a second poll for it. Okay, so no no's. So perfect. So that's nice, because it means that our work can be useful for other folks. Are there any questions with regards to this project? Suggestions? Complaints?
Yeah, we had actually just started to look at this at Microsoft. We were needing something for U-boot logs, and so this lines up with that. But we're also wanting to do something with runtime firmware log messages. So on ARM64 platforms where we have things running in like an OPT environment, along with the Linux kernel. Sometimes we have needs to be able to log verbose messages from those applications running an opt, and right now we're just writing to a memory region and collecting those at periodic times. But it would be nice if this wasn't specific to a bootloader, and it could be used for runtime firmware.
After discussion, thanks a lot for that comment. Could you leave send me your email? In general, our approach after discussion with other folks is that we would like to make this log format as generic as possible, and we would like to put this in a specification. We consider an UEFI specification, but the disadvantage of UEFI is that there's one of these disadvantages, is that we in general think that this buffer log format can be also useful for other systems which doesn't use UEFI.
Right. Ours would be used with device tree. We would specify a memory region in the device tree blob.
Yeah, so currently we are looking for other more generic places. Probably it will be tied to some extent with UEFI because, as you saw, we are using configuration tables. But in general, we are looking for a place for spec or a spec which is generic and allows you to use in projects regardless of type of firmware or BIOS or some on UEFI. So this is our plan. So if you can send me your email address, I will be happy to send the second version and to cooperate with you and others on this work.
Yeah, this is exciting.
Thanks a lot. Any other questions? We are almost out of the time.
Since this is the last session of the day, I think people could stay and chat if they wanted, potentially.
Yeah, sure. We just 10 minutes left, but I think that room can left longer than that.
Yeah, I think some of the micro conferences had like a informal after hours chit chat that just continued in the same room.
Okay, perfect.
Yes, you also have the hack rooms available, which may serve a purpose for under discussions, and it has the same capabilities as the micro conference room, so you can be a presenter, show some slides, etc.
Okay, anyway, I think that we have to wrap up at this point. Thank you for joining us this year. I hope the topics were very interesting for you and discussion around the presentations will help to improve the projects. Again, many thanks to our sponsors. I want to thank to Michał for helping me to leading this micro conference and Matthew for taking notes. And see you next year, I hope in better circumstances. But as Rich said, if some people would like to stay and chat about this and that, I'm okay with that. Just a reminder about chat, which is available here. Okay, bye guys.
One question is there a place where people could have these types of discussions outside of the microconference? Like, what's the best mailing list? Is it a TPM mailing list, or you know, the open source firmware Slack channel?
Rich, about what kind of discussion you're asking?
Just like, you know, the discussions on this microconference between now and next year.
I don't think that there is a mailing list open to participants. I will ask, Rich, I will ask about that, the organizers, and I will get back to you.
It's a broad question. Not only LPC, but just, you know, where in the ecosystem people would might want to meet up potentially.
Okay.
There's a few, like Linux integrity mailing lists. There's yeah, there's a few possibilities. It'd be nice to sort of pick one.
Okay, so you're asking about mailing list for discussion about different things related to the LPC, etc., between the conferences, right?
Related to this particular microconference, the types of topics specifically here. Yeah.
Okay. Okay, I will ask about that, and I will get back to you.
Thanks.
Welcome.